All right, we are live. We're good. It's all green, and it is good to see everybody here. And try to get the balance. I had requests for today because we're teaching. We've got the Siemens Motion Control 101. And it's really not just Siemens, but it is about really all motion control. And that's what we're talking about today. Welcome into the stream. It is our Friday stream, or at least what I try to always do on Friday. But yeah, my name is Jason Watts. If this is the first time you are to here on the channel, I am a CEO, owner of a little company out of the southern United States called Alpha Industrial Technologies. I live in the Atlanta area, and I have about a little over 20 years or so of industrial automation. Most of that, or industrial automation experience, most of that is in drives technologies. And so a lot of this channel is about the drives and motion technology, and today we are talking about introduction to motion topics, and we are going through and going to be kind of just going from a basic, kind of a general idea of what is motion, and then moving all the way up through some actual pretty specific Siemens technology objects using a 1500 processor. So a 1500, it's actually, we're going to be doing it on a 1515 TF. But the way that we're going to be doing it is you'll be kind of surprised that you'll be able to not just use just the drives that we're talking about today. You'll be able to use these concepts to retrofit into a system, any system that you're using a 1515 or a T processor on. So hey Christian, thank you thank you for at least sorry, thank you for at least joining in while you can. Yeah, definitely catch it on demand. Hopefully we'll have some cool topics, and yeah, so for yeah, as always, these are going to be available on demand. And if you're coming in and you're watching this on demand, maybe you have searched for some motion control support, motion control training, and you have come across here. Welcome to the stream. Hopefully, this will open it up to where it expands your knowledge about motion control. But then maybe you start kind of looking around on the other channel, and maybe we can earn a subscription, because for you to subscribe to this channel, because there's a lot of topics, not just about motion control, not just about drives. We talk about PLC, general automation, because yes, drives do move the world, but PLCs kind of got to be involved in there too. So we are getting in chat. Thank you for everyone that is coming in on live. It's great to see everybody. Oh yeah, I do see some faces I hadn't seen in a while. It's good to see you guys. Yeah, and always the easiest way to support this channel is to comment and like. So if you have a question, do not feel shamed or anything to ask that question. Drop it in a comment. If you're watching on demand, if you're here in chat, just go ahead and drop it into chat, and we'll try to adjust it. So last thing, we do have a Discord channel, and so Discord link is in the description too. So let's not spend too much more time kind of going through all this, because I mean, today what we are trying to kind of get around and do is, like I said, introducing these kind of topics about motion control. And the first thing that we really need to talk about is, what is motion control? Because honestly, depending on who you ask, depending on I guess the background that you have, there might be a lot of difference in what someone might consider motion control. So the first thing we want to do is kind of define what we're talking about today in motion control, because frankly, it's a little bit of a, if you only have experience with PLCs, you might consider anything with a drive or anything with a motor motion control. And in general, that's not quite what we're going to be talking about. In general, motion control will be any system that the actual position and control of the motion is vital for the process to handle. And so in general, like a fan process, not really motion control considered, because you don't really care about the position of that fan blade most of the time. You are just concerned about whether or not there's pressure or air or airflow or whatever. And so the actual motion, yes, obviously you're not going to get airflow without motion, but the actual position, the actual control of that motion is secondary to getting airflow. Same thing with pumps. You're trying to move some water around, not really necessarily motion control. Yes, you're moving water, but a lot of what we're going to be talking about, the concept that we're going to be talking about is positioning. And so for this conversation and for this discussion, we are going to say that everything that we're going to be talking about has position control. And you say, okay, what is that? Well, we kind of started, we'll start from where we kind of ended last week in our drives basic class, so the 102 class. We kind of got into talking about the concepts of different control loops inside the drives. And so you have a speed controller, torque controller, and we kind of talked about in that stream about the position controller and how it kind of interacts with the other controllers, the other torque, speed, and then position control. And we're going to be talking, everything that we're going to be dealing with is dealing with the position control and higher. And so there's a lot of kind of levels on top of that. So if you're unfamiliar with what I'm talking about, control loops, I would suggest at some point going back and watching the two previous live streams, or at least going through them and kind of like listening to the concepts, because it talks about like how drives do what they do, and then these concepts of control loops and what we're talking about there. So, but you can kind of maybe stay on this and glean a lot of information from this. But if you're completely unfamiliar with that, some of this might not make sense to you, but you can still get a lot from this live stream, because we're going to be talking about concepts that you may hear in industry. So what have been doing is kind of talking about, and I've got to get a little bit of music going, just something for me to keep my flow going. So hopefully it's not too loud for you guys. But what we have been talking about is previously in those streams is about the drives. Now we're going to talk about kind of like outside of our drive, what is happening in the real world, what is happening to our process, what is happening to our machine. And so ultimately, we talked about wanting to control like the torque and being able to accelerate and decelerate a motor. And in that, we used we had a current controller. And so you had the PWMs or PWM controller, and that goes out to your motor, right? We talked about this last week. And then outside of this, there is a speed ED controller, and it sends in a torque set point out of the speed controller. And so it has some stuff, feedback coming in. And then what we're going to be talking about from here has to do with an outside a further outside loop, the position controller. And ultimately what the position controller is going to be looking at is essentially the same thing. It's going to look very much like a speed controller. It's going to have a lot of the same features that a speed controller has. It is going to be looking at the speed, it is going to be looking at the position, which in fact that feedback just comes back from the encoder, and then it's doing a calculation, and we're going to be talking about kind of what are called mechanics and what you need in that. And so what we have is, instead of a torque output from our position controller, we actually have a speed set point. So a in set point, SP. And so that's what goes into the speed controller. So when you're doing a motion control project and you are setting up this position controller and you are wanting to control the position of a machine, you have to have a well-tuned speed controller. So one of the first concepts in motion control is, a lot of people want to start up at the PLC and start kind of doing all the fancy stuff that we're going to be kind of talking about today: gearing, camming, kinematics, like all the fancy stuff, positioning. Well, if you don't have a good control of your speed, you cannot control your system very well. So the first thing you have to do is go through and make sure that this system works really well. Last week when we were talking about the Drives 102 class, I said the torque controller kind of sets itself. It's pretty well tuned for an AC drive. Well, obviously the speed controller can have a lot of variance in it. There's a lot of things that can go on with a speed controller that makes it to where your speed set point does not follow, your speed does not follow your speed set point very well. And if you have a poorly tuned speed controller, then you will not be able to have a good position controller. And there's two things about this: that one, you could just have your settings off. Two, your mechanics can be just bad. Like if you have a bad gearbox, there is no amount of tuning, there's no amount of programming that will fix a bad gearbox. It's just not possible. So you can help make things not as bad, but the physical design of your system is going to kind of limit you on what you can physically do with a motion control system. And I know that sounds kind of basic and you're like, duh, but it kind of gets lost a little bit, that if you're going in and you're putting in a lot of equipment or a lot of money into upgrading controls, and you don't have a good, like your gearbox has a lot of backlash in it, then yeah, you're not going to be able to control. It doesn't matter how much you spend on SiMotion processors or 1500Ts or whatever. You're not going to be able to get the performance. Whereas if it was designed in order to, from the ground up, with the performance level that you're wanting in mind. So just be aware of that. Sometimes managers and things want to increase production, and they say, okay, what's the easiest way to increase production? Okay, well, I've watched all of these YouTube videos, and I have these LinkedIn articles about integrating automation and doing these sorts of things. And then they don't realize that they have a gearbox that hasn't been changed out since in 20 years and has so much backlash in it that like all of your settings, like you drift, and they expect you to perform a miracle. Well, we can't do that. So one of the things I was talking, kind of like bringing up, if you weren't, I do some kind of casual streams during the week, and in it we are making a Delta picker. So we're designing a Delta picker and 3D printing it. And last night, for those of, if there anybody that was on that stream last night, y'all should like say something in chat, because I left it kind of in the middle. I got pretty stumped in designing this, and this is one of the arms that we're designing, and we're making a kind of a slippering sort of thing so that this part will break instead of this part. So I'm not having to print out. So I'm not having to. I can only have to print out this part. Well, guess what? I have a fitted actual part. So perseverance. But the reason I wanted to show you this, because last night I did not have this fit. At the end of the stream, I was printing this out, but it did fit together. But I wanted to just kind of show you, just this looks like a pretty good fit, and you can't really see it. It's white and it's kind of washing it out, but you can kind of hear, kind of like going back and forth. You can hear this like rattling, and that sound. It kind of has like a rattle that's like back and forth in it, and that doesn't seem like that big of a deal. I mean, you're like, oh well, this is just going to slide off, which is true, but in the systems that we're looking at and how accurate some of these things could get, that little bit of backlash, we're going to talk about this probably at another point, but that little bit of backlash over time can cause incredible amounts of drift. And so you're sending out a system, or you're sending out a signal and say go to 100 millimeters, and the first time it might go to dead on 100 millimeters, and then the second time it makes it to 99.9999999 millimeters, and you can't even tell that it wasn't accurate. Well, it doesn't know. It's saying it's 100 millimeters. Well, over time, just the ever so slightest bit of backlash, every time, if you have backlash in a mechanical system, every time you reverse directions, then it is going to cause an error, because it thinks it is moving 1 degree out here, and it's actually only moving 9 or 0.99999 degrees. And then when it comes back, it thinks it's moving 1 degree back, but it's really actually moving 0.99999 back. And so over time, it works into where this thing will drift and it will be way off. So all that to say, on this design, the reason I did it this way was for modularity, but I'm going to have to get as much of that backlash out as possible. So just thought it was an interesting kind of real world kind of like principle. Now, we're doing this Delta picker, most of these, obviously when I do the actual metal version of these, I'm not going to use this. I'm going to use an actual keyed metal shaft, and then it's going to have a key on it and use the actual key of the shaft, and we'll go from there. So first things first, mechanical system really matters. And so, but yeah, if you have any like horror stories or anything, if you're in chat, definitely like put them in the chat, because like we're trying to kind of address different things, and the more that we communicate back and forth together and we share our experiences and all of that, then yeah, that's how we learn and grow. And so so the next thing that I want to talk about is talking about some of the different functions that we will be using. All of these are going to be using positioning, but there's terms that you'll hear a lot about, kind of like different terms of what type of motion you're trying to do. And so we will kind of go through these different things. And again, a lot of people have kind of like these different ideas about what constitutes motion. And so a lot of these different things, as they get more and more complex, nobody's going to say that a 3D delta picker is not a high-end motion control problem. But some people might say, well, I'm just positioning a conveyor belt. That's not really motion. I'm just moving a box to a station. And honestly, the simplest position control system actually is just a limit switch. So you run your conveyor, and so you have a conveyor with a limit switch, and when the box moves up against it, it hits the limit switch and stops the conveyor. And so that is a very simple positioning circuit. So because here's your feedback, and then your speed set point is either 0 or whatever the speed set point is. And so when you get your feedback to say stop, it stops. Now think about this. If this conveyor was not able to stop quickly, then obviously the box would end up a little bit further down the line. And so that's just illustrating the concept of, if your speed controller is not able to handle your commands quickly, then you can't follow anything. So we'll talk about some stuff here in a second about how to set your drive up for that when we actually get into it. But let's talk about the actual different topics. No, this. Select all, delete, because what I'm going to get into is we're going to talk about, let me get everything set up to where I'm used to it, so I can see chat if somebody asks a question. Again, if you're joining in live, welcome to the stream. If it's the first time, we do these every Friday. We'd love to get everybody chatting it up and kind of talking. No, this is a little bit early for the US crowd, but we have a very international crowd on these streams. If you're watching this on demand, be sure to drop a comment to where you're from, just so that we know, just so that we can see how far reaching this channel can get. So let's talk about 3 different types of motion. What's up, everyone? And so the first we have talked about is just simple positioning. Okay, and so in the little thumbnail for this stream, there is a kind of a very simple showing of what positioning is. You are trying to, in some way, take your axis and move it to a position. It sounds very simple, but to be able to do that, everything else on this list of motion control functions requires accurate position control. And remember, I'm going to reiterate it again, you can't have accurate position control if you don't have good speed control. So positioning is integral to everything that we have here. And so this is pretty simple. So these functions would be like, Ignatius, welcome to the stream. Good to see you. Good to see you. Glad to see everybody coming in to chat. And like I said, I know it's a little early for the US, and it's kind of awkward in the European time zones as well. People getting off work and then people just getting into the groove on their Friday. But hey, you can always have an excuse here in the US to be like, hey, this is training. I'm learning stuff. And so that I need to take my lunch early, you know? And I mean, if you need your boss, you need a letter for your boss that you're actually doing something, maybe I can help you out on that. So yes, seeing more people from the stream last night. It's good to see everyone coming in. So positioning we kind of already talked about, these are going to be in our motion control blocks. These are going to be like MC move relative and MC move absolute. And let's just talk about these two moves for a second, because it's good to understand kind of the difference between the basic moves, and positioning this concept of relative versus absolute goes a really long way and builds up in all of the other ones. So a relative move means essentially, if it does not matter where I am, start at wherever you are and then move a certain amount in a certain direction. So say this is 100 millimeters. Well, this would be, it does not matter what's back here. It does not matter where you are. It does not matter where you have been. It only matters that you move in this direction 100 millimeters. So it should be a pretty intuitive that if you do a relative move, you may not end up in the same place every time. And so if you repeat a relative move over and over and over again, you will move 100 millimeters at first. So you'll move this first 100 millimeters. If you immediately fire it again, it will move another 100 millimeters. If you fire it again, it will move another 100 millimeters, and so on and so on. So that's a relative move. And so most people think, okay, I'm wanting to move 100 millimeters, so all functions are going to move 100 millimeters. Well, maybe not necessarily the case. Well, that is a move relative. So let's talk about a move absolute, because a move absolute, if you have the full range, say this is negative 1,000 millimeters, and this is positive 1,000 millimeters, okay? And we are sitting at 0. And if we are sitting at 0 and we say, I want to do a MC move absolute to 100, it will move 100 millimeters and then sit at 100. Okay? Fairly simple. If we say MC move absolute, now fire another one that says move to negative 500, which is down here. So this is negative 500. You say MC move negative 500, it goes from here, moves back, or move absolute, and we'll move back to here. So that's an MC move absolute negative 500. So it moves back, right? Well, what if I said at this point, I want to move MC move absolute negative 300? Well, should make sense that it's going to go to somewhere around here. It's going to move positive direction up to negative 300, right? So these are absolute positions. Now, if I fired that move, if it's sitting here at negative 300 and I say move to negative 300, it says, okay, done. And it doesn't move. And if you're not expecting that, and you say, no, move negative 300. And it says, done. And you keep firing this move absolute and expecting it to act to move negative 300. That's not an absolute move. That is a relative move. So an absolute move goes to an absolute position. It goes to a position. And so if you say MC move relative 0, the axis will never move, right? Because it's where you are, move 0. Okay, done. I didn't move at all. Sweet. Now, if you change that to an MC move absolute, if you're sitting at 0, nothing happens. But if you're sitting at negative 1,000, all of a sudden the motor takes off and starts going to 0 because you're saying, hey, move absolute 0. And it moves to 0. And so it would move back to our 0 point. So that's a concept of absolute versus relative. So we got a question in chat. So for them, both reference point is not at 0 and relative position is adding to final. So talking about the reference point. So an absolute move needs to know where it is. And so an absolute move has to have a reference point. So you have to say, hey, this is a fixed point in space. In general, most of the time, people set their reference at 0. Most applications, you set the reference point at 0. What's up, Lucas? It's good to see you. Good to see you in chat. And so most of the time, we set our reference point at 0. Now, like you kind of mentioned, relative position, you don't actually need a reference point because it doesn't care. Remember, it's up here. It doesn't care. Whatever. With a relative move, you're moving from wherever you are just to that. So it doesn't need to know where it actually is. It just needs to know how far it's moving. And how far it's moving is based on the mechanics that we're going to kind of talk about here in a second when we set up these technology objects. So just know that to do an absolute move, you have to have a reference point set, and that is using the MC home function. Okay, so you have to have an MC home. The axis has to be homed in order to do an absolute move, and I'll show you how to do that. But it's fairly simple because there's inside the technology objects there are homing routines that are built up into this, and we'll talk about that. So this is positioning. These are the two main positioning functions that kind of like they keep up with absolutely really everything. They're kind of like the core of motion control concepts, because everything that you can kind of bring down to can come down to these types of relationships. All right, are we relative to something or are we absolute? So are we in a fixed field of, like a fixed frame of reference? And I'm going to talk about that here in a second. Are we in a fixed frame of reference? Or are we in a relative frame of reference? Because that makes a difference later on when we are talking about these higher order functions. So this is kind of the basis of motion is position control. And here's what you got. So now I will say a little bit about, we talked about this in the, I can't remember if it was in the, yeah, I guess it was in the Drive 102 class. We were kind of talking a little bit about the different controllers, and the position controller uses what's called length units. So everything in here is in some sort of like physical length unit. And I kind of mentioned it here a second ago just about the mechanics. The gear ratio changes how, sorry, grab this little motor here. The gear ratio changes how many rotations of the motor, how that rotation equates to actual physical motion at the end of the thing. So let's stick this on here, if I can get it on here. and then slide this on here. A simple gear ratio. Obviously, this is not putting a gear ratio in here, but there is a rotation of this axis that this length here from these two connection points creates this circle, this radius. So if you want to actually say degrees, or not degrees are going to be the same, like a 0 degree and then a 45 degree pitch, like that's 45 degrees. But depending on the length of this arm, this distance up here is going to be different based on the circumference of this circle. And so that is kind of like a very simple ratio. So if you wanted to say, hey, I want to move so many millimeters out here at this edge, you have to know the length of this arm. Because all you know is the position of this. That's what this encoder is giving you, is the position of the shaft. And so how does that actually relate out into the real world? Well, that's based on your mechanics. And so that's what I mean when I say mechanics, and we'll talk about it, and we'll set those up here in a second. So we've talked about this length unit here is a millimeter. And depending on how your mechanics are set up, that could be a linear or a rotary system. So like that, what I was just showing you there it's kind of all in degrees. And then everything's on circles. And so it's a rotary system. And a lot of things that you come across, like printing presses or winders or things like that, there's a linear component to it, as in I'm trying to wind something up, but the motion is actually having to deal with rolls and the ratios and stuff like that. And so there's a little bit of nuance in picking, all right, is this going to be a linear system or is it going to be a rotary system? And that's one of kind of the things that if you're in a linear system, like, for example, if you have a ball screw and you have like a linear slide and you have a ball screw that's moving a table back and forth, obviously you want to take that position and move 100 millimeters, right? That's the whole point. Well, that's taking rotary motion and changing it into linear motion. And so that's a linear system that is in some sort of length units of millimeters. Well, if you have like a roll and you're positioning something on two rolls like this, that's actually degrees, because you don't too much care about a lot of times the actual how far this is going. You're just trying to match a degree. So like this degree point, you're trying to match these up like that right there. So we'll be talking about that. That's a rotary system. So, but everything's in length units. And to go from that unknown length unit to a millimeter, so like a generic length unit to a millimeter, that process is called normalization. And I don't know why you're normalizing your system to engineering units. And obviously there's a conversion between millimeters and bald eagle units. And so that's just a number. It's just like an equation between the two. And so that normalization is just you're multiplying in order to convert to the units that you want to use in your system. So that's what normalization is. So we've got, let me pull this, clear that, and we're going to move and we're going to talk about the next topic, and that's the concept of synchronization. Okay. And it's kind of a little difficult sometimes to think about. I'm getting my little gear set here. So we have two different sets of gears, right? We know if these were of actual a pitch that could interface together, we would know that if we put these two things together, they would physically not be able to move between each other. And because of the size of this one, if I put torque on this, it would get multiplied out by a gear ratio in order to the torque on here would be greater. This one would move slower because one turn of this is going to be say 10 centimeters, whatever it is, and then one turn of this is going to be 20 centimeters. And so it rotates this 10 centimeters, it only does half a rotation here. So if that is a 2-to-1 ratio, and I don't know, that's close, but if this is a 2-to-1 ratio of the circumferences, then 2 rotations of this would equal 1 rotation of this. It's just basic mechanical gearing. Everybody's seen all of the marketing people that put all the gears on their little marketing tabs, and all the mechanical engineers are sitting back and like, ooh, yeah, this was a marketing person because this gearing doesn't work. Because they'll put 3 gears together and link them all together, and you're like, yeah, that's called binding. But you've probably messed with gears, and so you kind of know this concept. If you have a bicycle, same thing. If you have a small gear on the back and small gear on the back, big gear up on the front, you're going to go fast because you're making this move twice as fast as this one. If you flip it around, put the smaller gear on the front, the one that you're driving, and doing that, you have a gear ratio that multiplies your torque. So if I'm driving my small and it's a 2-to-1 ratio, I'm going to be multiplying my torque by 2 over here. So I get double the torque, but half the speed. So on like a normal application, you might only need to use like a 1,000 RPM. Well, if I have a 2,000 RPM motor, I can get away with doing a 2-to-1 pulley ratio on my motor, and I can create a 2-to-1 ratio because if I never need more than 1,000 RPM, I can go with a smaller motor and just put a 2-to-1 pulley on it. And the reason I say a pulley is because a V-groove pulley, I'll show you this on the drawing. So if we have 2-to-1 here, and we have a V-groove, like what's called a timing belt style belt, the ones with the little loops like this, there's no backlash in this system. And so the only problem that you get into is the springiness of this. You could also use a chain, but chains are heavy, so that increases the inertia, so you lose a little bit of your efficiency of your torque. And so you have the tension there. The cool thing about this, though, is unlike backlash, a spring, if you push on it and you hit it, it's eventually going to go to its stable happy place, right? It'll have that oscillation, but then it goes to a happy place. We'll talk probably in the Motion 102 class about these oscillations because it's a little bit of an advanced topic that comes up in some of these timing belt things. The tension of your belt can induce issues in your speed controller. And remember what I've said many times now? If you don't have a good speed controller, if you don't have a good speed response, then you're not going to have a good position control. So if you have this sort of situation to where that's kind of how a gear ratio works. You are physically, if you're thinking about it, this physical point here is essentially physically attached to this point here on this axis. So if this is axis 1, axis 1, and this is axis 2. We could see that at this point, this belt is connecting. We're going to assume that there's no spring in the belt for right now. That this is connected, this point is connected to this point, right? So positionally, they are connected. Now, when you move this angle, say that's about 30 degrees. If this is a 2-to-1 ratio, you're going to expect that angular movement to be halved. So down here, you would only get 15 degrees of movement. So physically, they are coupled. And so the outsides of these are going to move the same linear distance. So you look at the ridges, think about the ridges on that belt, on that timing belt, and that ridge is going to stay physically coupled to that the outside, those circumferences. So you're physically synchronizing those outside points, and the ratio comes from the relative different sizes, and so they're physically coupled. So this is a concept that in the motion control is called synchronization. And it's, if you can get the physical analog, then it's a little bit, eventually the physical analog is it's going to be difficult to be there. But all of the stuff that, or most of the stuff that we have for motion control has the concept of a physical concept between it. So this is called synchronization, sometimes called electronic gearing or gearing, because if this were a gear like this, they would be physically locked together, and I cannot move this because it is bound to this other gear, and so it is geared together. And so this is called yeah, terrible. Sync. Synchronism. And then, or it's also called gearing. Okay. And the reason I bring up those two concepts is we have what's called electronic gearing, electronic synchronization. So this is the physical, what we have down here right now. That's the physical. And what we're going to be doing in our program is we're going to synchronize them electronically. And so think about synchronism or electronic gearing as taking and putting on a belt, and instead of it being a physical, we're going to tie, according to a ratio, we're going to tie two positions together in an axis. And then, so 1-to-1, if this were 1-to-1, if we have that 30-degree angular motion on axis 1, we would have 30 degrees angular motion on axis 2. So that's 1-to-1. If we had a 2-to-1, so a gear reduction, we would have the same situation like this. If we had a 1-to-2, we would have a gear increase, so like an actual speed up. And so it would double in the other direction, and so it would go to 60 degrees. Right? So this would be a 2-to-1. This is a 1-to-1. And this is a 1-to-2. And so that's how electronic gearing, the concepts of it work. Okay? So, awesome. What's up? What's up, everybody in chat? It's good to see everybody coming in. Yeah, if you're coming into chat on live, we're going to be going for probably at at least, I mean, knowing me, this is some of my favorite stuff. So we're probably going to be going for another couple hours. So if you haven't already, please hit that like button, get it out there to where more people get it out on the stream. Tell YouTube that this content doesn't suck and get it out there. And that's honestly spamming like emoji, the like love and like spamming stuff in the chat actually really does boost these live streams out in the algorithm. So anytime y'all are chatting, just like whatever about stuff, I appreciate it. You're supporting the channel. So awesome. Thank you for being there. If you're watching this on demand and it's helpful, like, and if you see the other stuff that's on the channel, feel free to subscribe. So we're talking about this electronic gearing, electronic synchronization, and this is kind of the integral part of everything else that kind of builds on top of this. Is we have a position on one axis, and we are linking it somehow to a position of another axis. And at its core, that's electronic gearing. We will talk about the two different types of gearing, because just like we have two different types of positioning, we actually have two different types of synchronism as well. So we have absolute synchronism, relative synchronism, and absolute synchronism. So relative gearing and absolute gearing. And yeah, they're kind of going along with that concept of positioning. So let's talk about MC gear in. Okay, this is MC gear in. This is relative. Okay, so what it does is, again, we are gearing in a position, and we're trying to say we want to link two positions of two axes together. All right, and then if you want to put a ratio in, you can. We're just going to kind of, for right now, talk about just 1-to-1. So everything that we're going to be doing right now will be 1-to-1. So you have axis 1. Say it is running at like 360 degrees per second. Okay, so that's a speed, but you're going through, and you would see on this if you were doing this like 0 to 360, you would see this axis would look like 0 to 360, 0 to 360, 0 to 360, 0 to 360, and you would see it like this, and this length here would be 1 second. So this is position, and this is time. So that's what that graph would look like. I kind of squished it a little there, but it would go to 360 and then back to 0, 360, back to 0. But it's moving at a constant speed. So when you're thinking about, and this kind of goes back into the discussion we had previously about the concepts of speed controller versus a position controller. Remember, to go from speed to position, you're going to be taking an integral. And so, or is that the wrong way? Anyway, there's a integral, a derivative kind of like between the two. So a speed would look, this would be a constant speed like this. But when you actually go to position, it's doing this kind of sawtooth wave. And that's because the acceleration is 0, and so you have a constant speed going through this little section right here, and so that's a fixed slope, right? So the slope of a position is the speed, and that's what we have here. And when it flips over to 0, that's just what it's doing here. So this slope on these angles are the same. So we've got these. Now that's A1 and it's moving, and we say, hey, we want axis 2, we want to gear in, all right? So this is the leading axis, and this is the following axis. And we're going to run MC gear in, a relative gear in. Well, what a relative gear in says, and so let me change and give myself another color. Can I give myself another color here? Nope, I need to give myself black. So we have axis gear 1, or sorry, axis 2. Axis 1 is the pink, it's running. Actually, let me get this a little bigger. I'm gonna clear all this, get a little bigger, because this is quite important. Because if you, between A1 and A2, this is the lead, this is the, lead, follower. Now, axis A1 is going, its position looks like this. On and on and on. So a relative gear in is essentially kind of like the relative positioning. It says, hey, I don't really care like what has been happening before. I just need you to be at this, I just need you to move to this position or move to a position. Okay. And so you could kind of think about it of it doesn't care the absolute position of the leading axis. It only cares that you start matching it. And so we're going to fire this function here. So we're going to execute our MC gear in right here. Okay. So axis 1, its position was sitting at wherever until this point. All right. It was just sitting still. It had a position of whatever. Doesn't matter. Well, at a MC gear in relative, so just a regular MC gear in, it is going to accelerate up according to its acceleration, and then it's going to match this slope here. And then it's going to start following that slope. Okay? So if you notice there's this gap between these two peaks. Right? There's a gap. Because it doesn't actually really care about where it's actually synced up. It just doesn't care. So it just says, hey, when I fired this function, just speed up, get moving at the speed. Remember, the slope of the line is the speed because we're in position. So the slope of the position is the speed. And so this slope here will match this slope here. And so now they're linked up. And positionally, you can sit there and say vertically, take a vertical line and say, all right, at this point is geared into this point. And then it's going to have the same speed, the same relation. Cool thing about the gear in is now if you take and slow down your I'm just going to put this on the screen down here like this. So if you take and put down and slow down the So if we stop A1, then that means A2 will stop. And if we speed up A1, it will stay synced in because you have this ratio or this synchronization between these axes. Okay, so that's now they're synced together, and they will, when one moves, the other will move, and it'll look like that on a position. So that's a relative gear. Essentially, it's, hey, when you execute the gear function, then it just speeds up, links in wherever it links in. It doesn't really matter where you're linked in as long as you're moving at the same speed and you just act however it is. That's a relative gear. So let's clear this and go and talk about an MC gear in absolute. Yeah, so we've got a question that says, in MC gear in, do you have the same rotation speed for the following axis? Yes, so in a 1-to-1 ratio, you would have exactly the same speed. And it's being processed by the position. And it's a little bit different than if you were just setting two speed set points to be the same. Because if they're in every little speed set point difference, so let me do this, show this. So like, so if you have a speed set point, or not a speed set point, but a speed actual value, like it's going to be looking like this. Right? If you zoom in, it's always going to be looking like this. Now, this might only be like 1 or 2 RPM, which would be like a few degrees a second, like very, very small differences. But kind of like we said with the backlash, this is like a speed backlash. Whereas if you have backlash in a gear set, that's a positional backlash. This little ripple is like a speed backlash. And so depending on how that ripple happens, you can actually get, if this is running a little bit slower than it needs to be to follow a position, then it's going to kind of get a little bit off of the position. And it may not ever come all the way up here. It might only come up like this. Right? And then it could speed up like this and then come down. And so your position is always going to be a little bit off if you're just sending two speed set points to two controllers and say, hey, I've done the math, I've done this ratio, I want you to run at these two speeds. So doing this in a position controlled loop, in a motion function, so electronic gearing, it actually says, hey, I don't care what speed you're running, I want your positions to be linked together. And so I know that sounds like I'm saying that the speeds aren't going to be the same. But if your system is actually working together, just like if you had a 1-to-1 gear ratio, like if I had two of these, which have something like this, pop. If you have them of the same length, then if this one turns at a certain speed, then this one's going to turn at the same speed, right? But they are positionally linked. In fact, because they are positionally linked, they're going to track their speed even better than if you were just sending them a speed set point and say, hey, run the same speed. Now, I will say from a controller level, like deep down, obviously they're going to be getting about the same speed set point. But instead of just getting the same speed set point, you actually have a higher level controller saying, hey, I need you to run to be at a certain position, and you're not at that certain position. So I'm actually going to send you a little bit higher speed set point so that you actually run the proper speed, because speed is degrees per second, right? That's really what it's about. And so it's positions in a certain amount of time. So yes, you will. Yes. I'll give you the simple answer. Yes. That was the more extended answer. So let's get rid of this. I don't think I deleted it. And then now we'll go back to this. All right. So now we have we're going to be talking about a gear in absolute. What's up, Ali Reza? Great to see you again. So I'm guessing you're off of work now. you're back at home. You're back in the grind. So we're talking about the MC gear in absolute, and so we're gonna do an A1. Nope, got that one too high up my head. A1, and then A2, and then so axis 1. We've got moving like this. Yeah. Okay. So now before we just said we don't care where you are. We just want you to at some point find and get to the right speed, and then once you get to the right speed, keep that position. That's essentially what a MC gear in does, which is a relative gear. A gear in absolute goes and you were actually trying to synchronize to a certain point degree. So you take on an MC gear in absolute, some of the things are so like leading axis gear in point, and then the following axis synchronization point. So there's 2 points. So if you are doing this by default, these are going to be like 0 to 0, okay? Because obviously sometimes your ratios, you're in different places, and that's kind of like a little bit harder to think about, and so that might be like a motion 102 type topic. But for in the simplest state, we're going to say we want to put 0 degrees at 0 degrees. We want to synchronize them to where the 0 points of these two axes are exactly the same. And so this axis could be sitting here, and this axis is kind of spinning around like this. And I'm gonna call you back. So we've got this spinning around like this, and this is kind of sitting here, and say this is 0. Well, what it's wanting to do when you fire it, if it fires it here, it's going to try to get synced up to where they start rotating at the same, like that, and it's 1 to 1. Whereas MC relative, if you were here, it's just trying to go the same speed. And so what that looks like on a graph of the position is, we're going to go black, and if we are sitting at some value, okay, and say this is whatever, 120. If you're sitting at 120, and this is the 0 point. I mean, it's kind of hard to think about, but you have your home position. So like you look at this guy, we're gonna call like our little key. our key here is our home position. And when the home position is at 0 degrees, it looks like that, right? And so as we start to rotate around, it goes 90, 180, 270, and then back up to 0. Or it goes to 360 and then boop, next thing is at 0. So, what's up, Action Vibes? I'm flattered. But we got, so this is axis 2. It has the same thing. So it's tracking its position by this point. And so that's what this black line is kind of the position of the key, if you think about it, on this axis. So say let's fire we do this again, and we execute this gear in absolute at that point, okay? So we know that it's going to be doing whatever it's doing, right? And we're going to parameterize it to where, sorry, I have allergies, and in the southern US right now, pollen is going crazy. So, like, that's why I'm, like, scratching my nose. But, so we have to parameterize how fast this axis 2, is allowed to move. And then we're going to give it kind of a time period that we want it to actually synchronize up. And so what we're doing is it will look like, well, yeah. So that's what it will look like afterwards. So it's going to be tracked directly. This is with a 0 to 0, okay? So, and this, no matter where we fire this function, it is going to track and then do the tracking. It's going to track in a 0 to 0. Those keys are going to, like, it's going to be moving around and then whack, and it's going to be locked in. Now, you can change these two ratios, or these two values here. Instead of doing 0 to 1, you might want to do 180 to 1. And so it's sitting here, and then this is rotating around. I have no idea if my brain can physically actually do what I'm about to do, but it links up, and then is rotating like that. So there's a lot more parameterizations in an MC absolute, because it's like, okay, well, like in this case, for example, like if we were to fire this function right here, are you going to allow Jacob? Jacob. So Jacob, Jacob, good to see you, brother. Yeah, Jacob is a real life connection. He's a great friend in real life. So it's awesome to see you. Is this the first time you've been on stream by any chance? You're gonna come on like the motion control. You're trying to learn this stuff. Hey, if you can get all the other plants out there at Mercedes to go full Siemens, like you can say, hey. Just say that you were studying for line 3, and like that's what you're doing. You're just trying to support line 3 better, because I mean it's all Siemens. So Jacob works out at Mercedes-Benz manufacturing facility that's just out at Tuscaloosa. So yeah, he's a great friend. We've known each other for a long time. I think this is the first time he's actually watched a stream, but yeah, so because he actually works, he has a real job. But yes, paint and body. There we go. We just need to get everybody. Everybody needs to convert to the German way. And it's funny, you might be like, why isn't Siemens at Mercedes in the US? But when they built that plant however many years ago, back when, like, even when I was a kid, they were like, you can't build this plant unless you use like all the other like manufacturers around in the area. So they've recently been converting everything slowly over to Siemens. So, um, yeah, okay. Let's get back to what we were talking about. So we're talking about like if we fired this this axis gear in absolute at this point, this it would need to travel backwards. So it would need to go negative down to this. Well, this the axis 1 is actually moving in the positive direction. So it's has this constantly gaining. So do you want to allow the axis 2 to go backwards? So like, do you want it to go backwards and then sync up, or do you just want it to sit there and let the other axis kind of like boop and then like catch up and do that? And so yeah, so I'm going to answer that, Nikos, like here in a second. So that's a parameterization that you have there as well. And so that is like synced up 1-to-1. And another parameterization would be if you changed this value, it would put a shift in this. And so it would take and say, okay, I want to connect my 120 degrees to my, I want to connect my 120 degrees to say it's 0. And so what that would mean is that when this is at 0, or sorry, when axis 1 is at 0, the axis 2 would be at 120. And so it would look like you'd have to extend this out, and it would essentially define that shift. And so it would look like this. And so the shift difference between these numbers would create a shift. All right. And so now Nikos has brought up the craziness. And so these are some of the kind of topics that you don't necessarily need to know, but just in these gear-in absolute functions, just know that you are actually setting a position on your following axis and tying it to a relationship between it and the leading axis. So I started working. So the question is, how many years of experience do I have in automation? I started working rebuilding drives when I was 14 because my dad had a systems integrator outfit on the side. I actually started programming drives and things like that when I was around 16. So I always say around 20 or so years of experience in automation. So that's kind of the big difference between honestly, like wherever you are in your setup or in your automation journey is like you're starting, and just be cool with being where you are. And if you've got 10 years of experience, try to learn. If you've got 0 years of experience, try to learn. If you've got 20 years of experience, try to learn. And you're always going to end up being better off that way. And I kind of talked about this in the last one. Like, you can always learn something from someone because they have some sort of perspective that you don't. Even if they are a person that has only ever been a janitor in their life, and they have trouble reading, you can still learn from their experience. Even if you're like a 20-year professional engineer, like you could still learn from their experience. So always learn. And these concepts here, honestly, are some of the things that trip up. And like, you can have 20 years of experience and never really understand the difference between absolute gearing and relative gearing. And you go to kind of implement these functions into a system that you're doing, and you're like, oh, well, I'm going to use relative gearing, and then you're not getting the right product results. And it's because you actually need things linked up. So Nikos asked if you can put a 1-to-2 ratio into gear in absolute. And so you absolutely can put this gear ratio in. And now my little thing is getting a little cluttered here. But if I wanted to put like a 2-to-1 ratio into this, so let's just say a 0-to-0, 2-to-1 ratio. That means that these peaks, so I'm going to draw this 2-to-1. Yeah, so if you want to join, there is a link in the description, or you can just hit the join, because we do have memberships. We're going to be doing a portal project here in a second where we're going to be building some stuff. The supporter level on this is the supporter level will get you data blocks, documents, things that we use. The programmer level will actually get you the all of the files that we create on the stream. You get that at the programmer level. And so, yeah, that option is available to you. And when you sign up, there is a Google Drive link that gets updated every month. And as I'm putting these files in, you can go on and click that Google Box or Google Drive link in the description, or in the membership level. So I'm going to attempt to draw a 2-to-1 ratio in this blue now. And if I do it properly, if I'm able to do it, I need y'all to like spam claps in the chat or something. So well, so Action 5 says, will I get support? So we have the Discord that has a bunch of people that are in the community that are international, that have all sorts of different levels of experience. I stay on Discord a good bit. And if you have a problem, if you have kind of questions, Discord's a great place to put it in there. We've got a bunch of people that answer questions in Discord. I can't guarantee you at any hour at the time, especially not for $5 a month. That is not quite feasible, but definitely will help you out. Try to enable you to do it. So I'm about to try to draw a 2-to-1 gear in ratio. So we're going to gear in. We're sitting here at this, and so we're going to gear in at this point just to make my life easier. And so we're going to be geared in here. And so it will have to be twice the speed. It'll drop there. I don't know how well I did, chat. It's so a 2-to-1, you would be essentially getting your speed in twice. You'd be getting 2 cycles like this. Oh, that was terrible. It went off the edge of my pad. No, get away, get away. Oh, that's hard. So that's what a 2-to-1 gear ratio would look like on this. So you would link up at some point. So at this point, 0-to-0, it's linked up down at this bottom point down here. And from that point, if it moves 1 degree, if the pink axis 1 moves 1 degree, the blue will move 2. And so what it ends up doing is compressing that sawtooth together. And what you will find is that this slope here is actually twice that of this slope here. So that's kind of the relationship if you were to do a 2-to-1 ratio. I guess this would be a 1-to-2 ratio. So your following axis, every 1 rotation, every 1 degree, every 1 length unit on your leading axis leads to 2 degrees length units rotations on the following axis. So that's the difference between absolute gearing and relative gearing. And the reason why it's important to understand the concept of absolute gearing is because everything else kind of builds on top of that. I'm about to talk about camming. And we're just going to go over the concept of camming because we're sitting at about an hour and a half, and I want to be able to actually do some programming on these things. And camming is a little bit more of a topic. There's a little bit more that goes along with it, just in terms of programming. And so, yeah, let's get music. And so, yeah, this is absolute gearing. And again, I probably will go more in depth because especially once I get the Delta Picker going and I have some actual stuff to work with. I can show you how these look in live, like actually online, actually tracing them. And that's really the way that this comes about. So we're going to clear this. And now I'm going to go back and look at because what I want to talk about now is it 2 M's or 1 M's, chat? Is it camming? Well, it's definitely not 3 M's. Is it cam with 1 M or cam with 2 M's? I don't know. I guess I could probably learn this, but that's how I'm going to spell it. It looks cool. Camming. Because camming is a form of absolute gearing, except where, think of it like absolute gearing. You're taking a position on, where's the O? Where's the O? There's no O. That's not an O. That's an A. So camming is a form of absolute gearing because you are taking just like the master axis or leading axis of old school version of words, the leading axis, and you are tying a position to a position. Okay? Well, in camming, that position changes. So instead of like having a gear ratio, you actually have what's called a cam profile, and at a certain position, the other axis will, or the following axis will come through and be at a certain position. So before, like in absolute gearing, if we did a 0 to 0 absolute gear, 0 and 0 were always synced like that. Well, and if we linked 10 degrees to 0, they would still be 0 to 0. Well, in camming, this following position, as this rotates, it can change, and it can do whatever according to a cam profile. And the physical analog to this is a really cool process that's actually the old school way of kind of doing an assembly line. You would have and I'm going to go through and kind of do, and honestly, there might be a lot of places that are still like this because it's actually a pretty cool, simple way to do it. You would have and when I say old school, I mean like 1800s. You'd have like a big steam engine with a flywheel, and then you would have a belt that would go up and loop over a big central shaft that hangs yeah, so if you sign up and you're at the programming level, like you're gonna be getting in the Discord, you're gonna be getting that feedback like back and forth. Like that's part of the stuff. Now, on that is the kind of benefits of being part of this community is we have a lot of yeah. So in the old way, we're exactly talking about this. So they would have a big like steam engine that would be running here, and they would be shoveling in coal into this, and this would be turning. So you would have your rotation, and it would come up, and this shaft would be rotating. Well, if you had a piece of equipment that was down here that needed to spin, you would just throw a belt up like this right here, and you would throw a belt over that shaft and gear it in, and then this would start spinning, right? I threw that the wrong way. So it would start spinning, and your piece of equipment would be able to spin, and it would be able to do its thing. Well, they found that what if I needed a plunger to go up and down and kind of go up and kind of do like this, right? So they figured out that if they put on, like if we zoom in onto this, if they put on this shaft, if they made a kind of a strange shape, I'm randomly drawing a shape. And as this is rotating, they had their plunger physically kind of moving along this shape. You could see as it would rotate, it would follow along this path. And so it would pull up, it would come down, it would pull up. So like as that shape rotated, it would pull that plunger up and down. And so it could regulate steam, it could stamp out, boom, boom, boom. It could do a multi-stage, it could do like a multi-stage like compression. So it could press halfway down, then come up and then press all the way down. It could do stuff like that. It could, and all from what's called a cam profile. Right, so that's the cam profile, the weird shape, and again, it kind of is like this is the mechanical, the old school way of where all this came from. Well, now with MC camming, MC cam, I think it's like cam in, and with this concept of motion control camming, we're taking and eliminating the physical and taking it into a digital, which is still called a cam profile. And we're going to look at it. But what you are doing is, if you have a 0, I'm just going to clear all this out and start over. It's getting a little cluttered. So you have welcome to the channel. We've got got a new member, new joining, 18 minutes lag, so hi from the future. Awesome. Yeah, so in 18 minutes, when you catch up to this, we're going to be celebrating new members on the channel. And yeah, we're kind of talking about the memberships. I was going to talk about them in a little bit when we started in the thing. So yeah, so we were talking about the memberships. I was going to talk about it later, but what you get out of that is like all of the documents. So at the highest level, you get all of anything we create on stream, you get access to. You can go through, modify it, use it, change it, do whatever you want, play around with it. But and then at the first level, just a supporter level, if we make a PLC data type or like a function block, like a utility block or something, you're able to get access to that. So we're celebrating our members, and it's great to see everybody that chooses to support financially this channel. The best thing that it does is that support goes so much further in the YouTube algorithm to get all this content out there. So I really appreciate everyone that it chooses to be a member and support financially. If that's not for you, still just subscribing and liking the streams and liking the channel or liking videos goes another much further as well to do that. So we're talking about camming, and this cam profile, this will be the leading axis position. So in ours, we go from 0 to 360, and this is the follower position. Okay, and this can honestly, this doesn't have to be 360. It can be 1080, 1000, whatever, because this could be millimeter, or this could be a linear sort of setup, and you're kind of drawing something. But what the cam profile and camming does is creates a relationship between the leading axis position and the following axis position. So if we were to have this right here, we would say the leading axis, when it is at 0, the following axis is at 0. We'll call that our origin, okay? That doesn't have to be the case. We could want, when the leading axis is at, say, 120 degrees. So let's 80, 90, whatever. So at 180, we want the leading axis position at 0. We want the follower to be at 180, and so it would look like this. And then we go through, and at different points, so 180, 90, 45. So we can go through and create these kind of like cam points. Say at 40, let's do it at this. Let's do 90. This is 90 on the leading axis. We want the following axis to be at 45, which would be somewhere down here, right? And then at 180, we want the following axis to be back at 180. And then at 270, we want it to be at 270. And then at 360, it's very close to 0. So we would want it to be somewhere close to this kind of the same position as 0, because we know that this is going to roll over, and we'll talk about why we want to do that here in a second. So camming, same rotation speed for the two axes, but different linear speed for the following axis in each angle. Not quite. So camming, remember all of these motion control functionality, the speed of the axis is going to be secondary to the position of the axes. So in this whole concept of like motion control, the speed has less to do with the position, or sorry, it has less importance than the position. The position is what matters, even though, yes, it will end up being the speed, but I want you to think about everything in motion control as being centered around the position. You put limits on speed, you have to think about speed, but you are trying to control positions. And in camming, you are taking two positions and tying them, having some sort of relationship between the two. And so what's really cool about a cammed system is if you have two kind of like linear axes that are like, let me get these two, that are like this, okay? And you have one that's just spinning, okay? Just assume that this one's spinning. This one could actually be going back and forth and like rotating back and forth like that. But it could also go like back and forth. And so, and it's all based on this cam profile. And And so kind of Nikos is bringing up a kind of a thought, or I guess a little bit of a thought in the chat, just kind of the different diameters and different ratios and different things, those go into the mechanics that I'm going to show you here in a little bit. But you have to do what's called normalization, get everything packed together to where when I say, hey, I want to have this at this position in my system, there's all sorts of gear ratios and everything that come down to ultimately you want this point to be at a certain point at a certain time. So on this cam profile, we have set up this leading axis position at 0. The follower is at 180. Now, the way that it kind of does what's interpolation between these points. And so I'll just do kind of a simple kind of interpolation. And we're going to just kind of go through and look at it like this. So in this one, think of the axis rotating, okay? So that this axis is just going from 0, going forward, 180, 270, 360, 0, 180, 270, 360, okay? So that's the leading axis. It's just kind of spinning like this. Well, at this, see if I can follow it. So this is going to be at 180. As it spins forward, it's going to come to 90. Or sorry, at 45 at 90. So it's going to go like that. And so when this is at 90, this is going to be at 45. And then at 180, they're going to be at 180. And then this is going to go at 270, is going to be at 270. Right? And then when it's getting close to 360, it's actually going to go back to 180. And so now we are at our starting point. And so as this goes back, it's going to go whoop, back down all the way through, and then back to there. And so this is this is going back and forth. So again, very much difficult concept to not see in person and not see kind of like in motion. That's why this is a little bit more than what a motion 101 class is. And the thing about it is there's kinematics that takes this and essentially takes this concept and makes it even more on top of it. So Holly Reza asks, position could be absolute or relative between master and slave. Yes. So in the camming profile, you can absolutely get you can you set this relationship based on this cam profile. And so the way that you set up camming is you create this cam profile, and then you create the cam profile, and then you attach the axis to the profile. And so you take, and just like an MC absolute gear, so like an MC gear in absolute, it's doing all this speed up and slow down in order to all these functions in order to kind of gear into that position. You attach your following axis to a cam profile. So position controller, position function is kind of the basis of all motion. Gearing ties the position of two axes together. And then on top of that, camming ties the position of two axes together in a programmable way. And so the relationship of I am at this point and now I am at this point is now relative based on a cam profile. And so Kinematics takes it one step further, and that's definitely going to be for motion 102 for sure. So yeah, we have got, so we're sitting about an hour and 45 minutes. I feel like a pretty good up to this point. So I'm pretty sure that is what I wanted to talk about. See if there was anything else that I wanted to talk about. Up here. No, not that. Go back to studio. So yeah, I'll give y'all a little time if you have any questions about that. Feel free to ask, like if you're in chat. And again, if you're watching this on demand, drop it in the comment. Drop a comment. You can do it that way. If you don't have Discord channel or Discord server is in the description as well. If you have Discord and want to use it, we've got a pretty cool little community going there. So it'd be cool if you join that. So let's see. We have talked about, so we've talked about all these different functions. Okay. Yeah, positioning, gearing, camming, and kinematics. I've talked about the different functions on another stream. So like advanced motion, advanced technology objects. There's a stream specifically already out there about kinematics. If you just can't wait, you could definitely go out there and get that. That is definitely there. Not one of them. So Ignatius has a measuring stream. There's a paper cup dosing machine called a tensor. It turns out one of the levers holding the cam was out, so the position to suck out of the paper cups is wrong. Yeah, so Ignatius is actually bringing up a really cool, kind of example of exactly what we're talking about. And so he's talking about a paper cup dosing machine. So like in bottling and dosing, you have these geared in axes that we're kind of going to be talking about. You have a conveyor belt that's running along, and you have this cup that's kind of like moving along, and you want to go down in and out and pull out like as it's going along. You're going to come in and out like that, and that's based on a cam. And so if that cam is off ever so slightly, so your leading axis down here is further ahead, that means that you're not going to be far enough down before you start pouring. So if this gets too far ahead, it's going to be way up here, because it's going to say, hey, I want at 3 inches, I want to be at 2 inches, 4 inches, I want to be down here like that, and then come out. And so if you get this cam profile off, then you will shift backwards. And in a mechanical system, it can literally slip on that shaft, and then it'll get off, and that's what happens. And so you have to actually turn that cam profile back, and as you rotate and move that cam profile forward, by rotating it on the shaft, it will actually advance where the position of that nozzle coming in and out is. The same thing, the equivalent of doing that would be taking, like on this, and taking and shifting this profile. Whoops. Hold on. So taking and shifting this profile like this. So and so shifting in time like this, like that. And so that shift makes it to where on the red, when the cup is at this position, the red has it at a lower speed. Okay, so it's lower. And so shifting it forward in time, or I guess backwards in time, if you want to think about it, it actually pulls everything up. And so shifting that whole cam profile, the cup is in the same position, but now you're at a different point in your cycle at that position. So that's the kind of electronic equivalent to taking a mechanical cam. So you have a weird cam lobe, and it has slipped on your axis. And so that's the same concept there. So very good example. I love getting like real world examples and talking about stuff like that, because ultimately that's what we're trying to do here. I do want to, I mean, my wife probably says I like to hear myself talk, but and she's probably right, but I like helping you out even more. And so if you have questions, if you have stuff like that, especially if you're in the chat, then like bring them up, because we're going through, and if you have examples that are like that, that is the best way to kind of get people to visualize. And honestly, you can go through now and you're talking about a bottling machine and you're like, what was he talking about? Go look up a video for a bottling line and like look at the cool stuff about it. And those bottling lines are using gearing and camming. And so, yeah, I appreciate it. I appreciate the compliments. I love doing this and teaching. I always talk about it. I had a leg up in life because of my dad was able to teach, and he was able and willing to teach, and he just loved teaching. And so any question I had growing up, he actually would give me a real answer. And so I always say it's like, when every kid asks why is the sky blue, and most of the time it's like, because God made it that way, and that's at least the Southern response. But my dad would be like, well, it's because the varying densities of light refract different wavelengths of light, and that's what actually gets to our eyes is the blue, and it's refracting off all the other ones because of the density of air. And I'll go, what's a wavelength? And he would go through and explain it. And so we would have these like conversations back and forth between just like how the world works. And so that's why I love doing this, because I mean, honestly, it's kind of like comfort food for me. I like being in these kind of conversations and helping people out and helping explain things. So I get as much out of these streams as you guys do. And so I appreciate everyone that comes in with kind of that learning attitude. So we have got, I want to bring up now, we're going to go over to Portal. And I'm not going to lie, I've already started on, I've already started a little bit on this. So am I in the right spot? Yeah, I'm in the bottom left. So I've started on this one. And again, like I've said before a couple times, if you're at the programmer level, you're going to get these files that we make afterwards. So I want to try and put as much as I can into them as like different examples. And so honestly, Ignatius's his thought of kind of this cup filling line is actually a really good idea. And so originally I was going to I was trying to think of a different concept, because what I brought in here is so I brought in a PLC 1515 TF, and then a S120 system and a V90 drive, because I wanted to show kind of, in my mind, it actually was kind of what Ignatius was kind of talking about. And so I'm going to go through and change one of the names of this, because I think that we have a better option. So on a bottling line, you have a bottle capper. And so you have a bottle coming along, and then you have a cap coming in and popping in. And so let's kind of like set up just in general a way that we could set this up to where we have the cap line, which is running off the top. So the bottle caps are on a separate axis. The actual bottle line is down on the bottom, and then the actual cap is gonna squish down, and we're gonna have like a little plunger that's like, you wouldn't really want to do it on a bottling line because you'd have to have a bunch of these, but we're gonna have an axis that gets extended down by our little V90 and plugs it down into the cap. Okay. And so we're going to do this. We're going to do convey or cap. And then we're going to do conveyor model. Well, let's do Ignatius's thing. So cup conveyor. And the cool thing about it, I'm going to show you here, technology objects are what are called, a fancy way of saying they are device agnostic. So you can set them up with different devices and use the same code. So, and I wanted to explain that because like the drive filler. And the reason that is the code that we would write today. I mean, I don't know how far along we'll get, but we'll definitely use this code in Motion 102 as well when we actually go through and do the actual cam profiles. Not going to do that today, but we will set everything up for the cam profile. The cool thing about it is once you set these up, if you wanted to do this on all V90s, you just change the hardware, and then I'll show you where to point the different axes to, set them up a little bit differently, and you just kind of go through the technology object setup. Your code stays exactly the same. So if we were to actually, I mean, this won't be fully fleshed out. It'll just kind of be examples of stuff. If we were to actually build out a full program that had everything, and you had a customer that was like, hey, I don't really like Siemens drives. I like ABB drives. And you're like, okay, can ABB, does it have a GSD file for a Telegram 103? And they're like, oh yeah, or not a 103, but a Telegram 3. And they're like, yeah, it does. And you say, okay, cool. And you're like, how much extra is that going to cost? Nothing, just the cost of the material, because you're not even going to have to barely change your code. You're just going to go through and import these GSD files, which I'll show you the difference. So the Siemens S120 is actually in Portal. It doesn't have to use an external software package to program the drive. The V90 is not that way. At least in the US, the V90 is not that way. You have to use what's called a GSD file, a general station description file. And it tells the PLC how to communicate to that drive. And you have a GSD file, and then you load in different telegrams into that GSD file. Now, you're not, I can't program the V90 in Portal, but I can absolutely use technology objects to control that V90. And so once I set up that software with vAssistant, you go through setup, tune the motor and everything, then you can control that drive with the technology objects with the same code that you can control with anything. Well, the only difference between a V90 code in this example and a ABB drive with a GSD file is the picture on the GSD file. Like, it's really not anything. As long as the mechanics are the same, you go through the same process to set everything up as you would in the V90. And so we're going to do that here. So talk a little bit though about the different functions that we're going to be using. So I have in here a 1515 TF processor, which is a technology safety processor. The reason I picked this TF is because that's what we use at Alpha. And so we use that as kind of our mainstay PLC, just because if a customer needs safety, we can have safety on it. If they need a technology object, they have technology object. And we generally designed around safety functions, so we use those. And if we don't use those functionality, we can kind of use it for other horsepower sort of stuff. Like we have a little bit of extra power for stuff. So that's why I picked the 1515. Now, a T designation, absolutely think technology. It is a technology CPU. But you do not have to have a T CPU to use technology objects. You can actually use technology objects on a 1200 CPU. The problem is it just eats up what are called motion resources. And the lower performance your processor is, the less motion resources you have. Now, I say that not all functions are allowed on a standard 1515, or sorry, a standard processor. There are some functions that require a tCPU. So let's go through just overview of those. Speed, technology objects, PIDs, all of those things, just in terms of motion control, speed axes, position axes, synchronous axis, and relative gearing is all available on a regular processor. So you're not going to be able to do gearing very well on a 1200 processor, but most 1500s will be able to do relative gearing on a couple of axes. When I say a couple, 2 or 3 shouldn't have any problem, even on kind of the lower end. If you have a higher end, like a 1516, 1517, you have more motion resources. You could probably do 10 or 12. Like, there is a document that we may go through to actually that I've gone through before that details out those specific limits. But I just mentioned it here that you do not have to have a technology processor to use technology objects. If you don't know which processor to use or whatever, reach out to your local Siemens sales representative, either distributor or whatever. If you don't have a good contact with Siemens, join the Discord, drop a comment on this video or another video, and I'll help you out. But just know that for the higher level stuff, so absolute gearing, camming, kinematics, those do require a technology CPU. That's why I have the 1515 TF in this one. And that is also why I stock and have standardized on these projects for the 1515 TF, is because if I need to have absolute gearing for some odd reason, I just throw it in there and use it. There's a separate section of motion control resources that are reserved for the use specifically in a tCPU. So it just keeps me out of trouble. So now we have kind of talked, especially in the advanced technology object section, we have talked quite a bit about kind of like speeds and kind of like the closed loop cycle times and how to optimize that. So I'm not going to go into any of this right now. I'm going to show you how to set up these objects in order to get to where we can get things set up for camming. Okay, because camming requires a synchronous axis. Okay, we have to have an axis that can be synchronized, and we're going to work our way all the way up. So first thing we have to do when we're setting up one of these systems is we have to determine which telegram we want. We talked ad nauseum about different telegrams, but telegrams are the way that every drive communicates to a system. So if you are only ever going to use Siemens technology, then you might consider other telegrams other than the standard telegrams. So what I have pulled up here is the list manual for the S120 drive system. And in the Profi drive, so section 3.9, it goes through and tells about all of these different telegrams. Well, the telegrams, if your number is less than 100, they are a standard telegram. And so that would be something that ABB would use, Yaskawa, Omron, Emerson, like whatever. All of these different drive manufacturers would have a Telegram 1, a Telegram 2, and as you can see, for servo control, Telegram 3, Telegram 4. And so, first thing that comes up that I mentioned, you're like, wait a second, servo. If you don't know what servo control is, definitely check out the basics of drives. So the Drives 101 and the Drives 102 live stream, because we talk about the difference between servo control and vector control. And in this project, we're going to be using servo control for everything. Now, that does not necessarily mean, as always, that we have to use a permanent magnet servo motor, right? Like this guy. There's a permanent magnet servo motor. There's neodymium magnets on the rotor. This motor has to use servo control, but you can always, well, not always, if you have an encoder, you can use servo control on an induction motor, and you can get pretty decent performance out of it, especially if you're using an induction motor like the 1PH8 servo motor that's by Siemens. All that to say, the way that you can tell what mode you are in on an S120, because an S120 can be either servo or vector, is you go to the actual object itself to where you pick the motor module. So in this, the conveyor, the cup conveyor and the conveyor filler, they have these little black boxes in them. I've brought in single motor modules. If you're interested in learning more about the S120 setup, there's more videos about that. But I click on it, and here the selected drive object type I have as high dynamic, as servo, and then I select my book size servo 18 amp book size module. Now I will say one thing. On a control unit, so this control unit has the control for multiple motor modules. Well, you can only either run vector and volts per hertz, or servo and volts per hertz on one control unit, because one control unit controls multiple motor modules. Those motor modules have to be running in the same control mode. Volts per hertz, everybody, like all of them use volts per hertz. So if you just have like a fan that just needs to be turned on and run, you can do that in volts per hertz. You could set it. And that would be under universal. Actually, no, sorry. That'd still be under high dynamic. You would just say in it to run in volts per hertz. And the reason I say that is if you get into where it will let you hear, and I don't know why, it will let you pick universal versus servo. It'll let you pick it. It's just at universal, it'll get swapped over into volts per hertz if you do that. And so you're not actually getting vector control and servo control on the same control unit, just so you know. So both these servo, obviously the V90 has to be a servo because it's using a 1FL6. It's a built-in motor. It's got its encoder. It's got power cable built in, nice and neat. So let's go through, and just so that in the future we can have this, yeah, right. So Lucid is saying Siemens should absolutely go through and say, hey, tell you that as like a warning when you do the compile on the project. But it actually only warns you when, or it just fails on the download. And when you go to download to the control unit, it just says, hey, this doesn't work. So yeah, I agree. There should be a little bit of warning, but honestly, I mean, nothing against Siemens in the way that they designed it. Portal in general is designed, I have found, from a PLC programmer's perspective. And so I don't know if that's just people that have programmed and they haven't really done a lot with drives. Maybe they don't even realize that that's an issue, you know? And it's like, oh, hey, well, whatever, like it's fine. Who would want to do that anyway? And they don't quite understand, whoever was in charge of that little module and that feature didn't quite understand the significance of it. But yeah, so I've got this system set up, a 1515 TF, an S120 with 2 axes, 2 18-amp motor modules running in vector. I threw, if you notice in this, I just threw a drive click motor over onto this. And the reason I do that is drive click is a kind of a RJ45 type Cat 6 style connector, and drive click encoders automatically fill in their data when you upload them. And so the reason I do that is so that I'm not having to go in and make up data about some motor I don't know anything about in order to just program this thing. If you put in, just drop in, say, hey, drop in a drive click motor, you can go through and program everything and it'll compile and it won't complain, because it's expecting, oh, hey, the first time I go to download this, I'm going to read out all the drive click. I'm going to bring it back in. I'm going to set all this stuff. We're going to be cool. You're going to be good. And so it lets you do a lot more without setting up that motor. So that's why I just throw a drive click motor in there. And on this little, can you see it? Yeah. Down, I guess down there in that, over on that other side, it's showing that a drive click motor that looks like a 1FK7 servo motor, like permanent magnet servo motor, like a big brother of this 1FL6. But that could be a 1PH8 has drive click. It could be like a linear motor. It could be a one of like the spindle motors, like they have drive click versions of them. So lots of different options. Don't think that you have to use a permanent magnet motor on an S120. Good. 2 hours. I don't know. So let's get moving. So next thing we got to do, like I said before, we got to pick these telegrams. So a lot of times I like to use the Siemens telegrams, which would be like these 103, 105 right here, just because there's a little bit extra data. So like 103, for example, the standard telegram 103 doesn't have this second encoder. So you can actually set an S120 up for multiple encoders, and whereas it's not guaranteed on other stuff. So this 103 allows a second encoder. And that's, I think, the biggest difference between 3 and 103. Yeah, it is. It's pretty much that's kind of the biggest. You might have a little bit of different status, but for the most part, it is the same. So we are going to use this telegram 3 just because for any positioning, you need to have, so for any motion control, you need to have the position. And this G1 X instantaneous 1, G1 X instantaneous 2, that is the position value. That's kind of like the encoder feedback that's coming back from this drive. And so that's what that is. That's why you have to have that. So you would be able to do any motion control with anything that has that G1 X Xis1. So telegram 3, telegram 4, telegram 5, telegram 6, you'd be able to do it. Yeah, all this other stuff doesn't look like you have the some maybe on that one. So that's just how to kind of interpret these. Now these 80 telegrams, again, they're standard telegrams. They're telegrams specifically for encoders. So you can set up this to run from an external encoder. We'll talk about that kind of on our, I guess that's probably a good thing to talk about now. No, we're talking about like mechanical systems. And remember, your feedback, if it's on the motor encoder, then it has to go through all of that, all of the gear ratios and all of that stuff. And so a lot of people will put what's called a process encoder. And so or a line encoder, and you'll put an encoder on the line because you're actually wanting to control like a conveyor position. Well, they'll put the encoder on the shaft of the roller for the conveyor, which in general guarantees that no matter what you put out on the like gear ratios, whatever slops there, it's going to position out here. The problem is your position controller can cause some really crazy instability if you have slop or bad mechanical systems, and you just be like, oh, well, I'll just put a line encoder on it and I won't worry about all that backlash. No, it's going to cause major problems. Just trust me, it's going to cause major problems because you have all this slop and the position isn't moving, and the position controller's like, oh, hey, put out more speed, and it's like, bah, and then all of a sudden it catches and then goes. That's a problem. It's crazy. Anyway, those are your motor encoder or your external encoder telegrams. So we're just going to use standard telegram 3, this telegram 3 here. So let's go back to portal, and in here we have 2 telegrams. So we have the conveyor cup, the conveyor filler, and we're just going to select 3 for both of them. And the reason you need to kind of know ahead of time what telegrams are appropriate is because if you don't have appropriate telegrams, then you don't have they won't show up in the technology object configuration. I'll show you on a GSD file how to actually change the telegram on a GSD file. Here, I have this GSD file that I imported. Network view, I went down here. I had already downloaded this GSD. I went through other field devices, Profinet IO, drive, Siemens AG, Dynamics, and then scrolled down and drugged my Dynamics V90 over in here and linked it to the Profinet master. Now I'm going to click on it and go to device view, and what over in the hardware catalog, under submodules, you have your telegram options. And so I want to use that same telegram 3, and it highlights where it can go. And then that sets up that telegram 3, and it goes through and says, all right, we're going to set all this stuff up in this. Probably not going to have to mess with this sort of stuff, like the starting ending addresses, just use it. But if you do, this is where it is. So we'll save. Another question. I appreciate it. I appreciate everyone that all the thanks and love in chat. Yeah, you guys make it worth it. Like it. If I was just sitting here talking to myself, then I'd probably be doing something different. So I love that y'all get on the chat and participate in this stuff. So really appreciate it. So we've got our network set up. We've got our telegram set up, because as long as we have telegrams, then now we can go through and yep, 3. We don't have to have this drive control telegram. That is for the control unit. We might use something on that later. If we change it, you see how these addresses over here kind of stack up against each other. If we change that to something bigger, it'll reorganize everything and put that into different addresses, but it'll update it automatically. So it's nice in that much. So let's go through and let's create our technology objects. And again, I'm going to kind of blow through these really quick, but I want the main conveyor axis, okay? And I want it to be a positioning axis. Now, here's the thing. You might say, oh, the reason I'm picking that is because I need a position controller, right? I need a position controller because we are doing, I need a position controller, so I got to use a positioning axis. I mean, you are correct. We need a position controller, but all of these technology objects have a built-in position feedback as an option. So you could use a speed axis for this. The only problem is a speed axis, you can't use the commands like MC move absolute, MC move relative. So like in our cup filler line, if you wanted to just have like a next position move to where you're kind of like toggling from cup to cup to cup to cup like that, you wouldn't be able to do that with a speed axis. You wouldn't be able to just say, hey, move 100 millimeters. But you wouldn't be able to do that. You can still link in a synchronous axis to a speed axis. So, yeah. So Ali Reza bringing up a point about Siemens 105, Telegram 105, and absolutely, Ali Reza, I agree with you that 105 is a much better telegram, but 105 is only available for Siemens drives. So just kind of in general, yeah, this is a Siemens channel and in general, but these technology objects can work with other drive manufacturers. They, as long as they have a GSD file with a Siemens or a Telegram 3, this program would be able to be set up and be ran. Whereas 105 is absolute better because Ali Reza mentions IRT and DSC. So IRT is isochronous real time, or some people say isochronous real time. It is just on the Profinet bus. It is actually a dedicated real-time communication to where you are getting your updates on a certain update cycle. That's IRT. DSC is so we're going to talk about torque limit. Ali Reza. But DSC is drive servo control or distributed servo control. I can't remember what it is, but what it does is it takes, and instead of having the position controller in the technology object, it still has the same inputs. It still has the same kind of control, MC home, MC power, MC move absolute, all the same MC functions, but the actual position controller is done down on the drive itself. So instead of the PLC sending a speed set point, instead of sending a speed set point, it sends a position set point. And the advantage to that is, I mean, you can get really fast update times over Profinet, especially with IRT. But if you put the position controller on the S120, you are actually able to get down to like 32 microsecond update times on that position controller. And so you can get incredibly tight, responsive position feedback. So on like a Delta picker, for example, DSC is going to give you a lot higher performance. If you're using Siemens motors and Siemens drives, it is going to have a lot higher performance than if you use just a standard Telegram 3. So great, dynamic servo control. That's it, dynamic servo control. Great point, Ali Reza. That's a great thing to bring up because my kind of like the first, I don't know, like 15 years of my, no, probably more than that, probably 18, 20 years of my career, I primarily used onboard position control. And so I didn't use all of these higher level functions. I was doing positioning in the drive. So DSC. And you can kind of get used to having that extra performance if you're not careful. Now, there's a lot of technology in the motion control stuff that kind of, most applications you don't really need that DSC because it's doing interpolation and all sorts of stuff in the PLC that kind of handles a bunch of stuff. But yeah, so 105 has that option for DSC. So we got a question also, is there a telegram that includes torque set point and process value? Yes, I'll show you. So there is and we're going to be talking about torque control or torque limiting and stuff like that. There is a telegram. Which one is it? So this DSC has torque in it. So which one is it? Sorry, there is one that has it in it, like built in, at least the current set point. So I know on where's 352? 352 has it right here. So current, torque, instantaneous, but that is for kind of a speed control axis. And so we don't have the G or the encoder feedback. So this I instantaneous, M instantaneous, those are the current and torque feedback. And in 352, you have all of these user words that you could set. And I actually have a data type that I have. I call it my agriculture 352 that has torque limits built into it. And I just connect those in all of Alpha's agriculture stuff, just in case we want to do some like torque limiting on a motor for some reason. But there is also I don't know if it's in here. There's a Telegram 750 that we're going to talk about that actually has and ties in torque limits and torque control, not torque control, torque limits, and then the torque feedback is available in 750, and we're going to talk about that a little bit today. But let's set up these. Let's set up these. So we're going to do a positioning axis on the main conveyor. And we're going to go through and kind of blow through this. Let's scroll this down a little bit. Select our drive, Profinet IO system, and then main drive. Never mind. So that's the CU, and then we are wanting the conveyor cup. Okay. And then it should populate all that. We're good to go. We'll talk about setting all that stuff up later. Let's go add a new object. We're going to do the filler. Let's do it this way. We said main conveyor. Yeah, filler conveyor. We are going to need that to be a synchronous axis. So in order to sync up anything, we have to use, for gearing or anything, you have to do a synchronous axis. And we're going to have that bottom conveyor doing its thing, and then we're going to sync it up, and I'll show you how to get that going. So same situation here. We're going to go here, Profinet here, then conveyor filler. And the next thing we need to do is in the leading axis. So possible leading axes, you have to set this here. And so a couple of other things, and we've kind of talked about this before. If in your synchronous axis, when you're setting up the available leading axes, the set point, you are saying, all right, I trust that the mechanical system is pretty stinking good, and so I'm going to look at the set point. And the reason why you would do this is because a lot of times you don't want to go off the actual value because it's going to have a little bit of jitter. And then if you're trying to tie off of a little bit of jitter, and then you're trying to tie off to a little bit of jitter, then it's going to be obviously that little bit of jitter turns into a little more jitter on the following axis. And so it makes it a little bit more difficult to be stable. And most of the time, stability is better than accuracy. And so, and most of the time, you're going to have a properly sized system. But if you don't, then you can actually go through and set this type of connection to actual value, just in case there's some sort of lag, inertia, whatever, that it doesn't always follow exactly how it wants. You want it to follow the actual value because you want it actually linked up to wherever it is, no matter what. That's the actual value. Most of the time, though, actual value causes instability in the system. So if your process works with a set point, then use a set point. But that's it. And obviously there's all sorts of other stuff that you have to set up that we'll set up later. But so that's that. So now we have we want to go through in our filler axis. it is going to have to be, so the actual up and down, we're eventually going to want to cam that. So we're going to do the synchronous axis on it as well. It pulls it up. Yeah, technically, Alirez is asking if the leading and following could be in two different PLCs, and yeah, it can. It's a little bit more difficult because you're having to essentially send the telegrams back and forth. You're having to send that relationship back and forth. But as long as you're sending that on an appropriate cycle, and you can absolutely set it up to do that way. It's just, yeah, probably if you can handle it, yeah, don't do that if it's possible. And so what I did there, my drive filler, the reason it looks different in that connection is because, well, it's a GSD file. And so it's saying GSD file, what telegrams are available in that GSD file, and then going down, and that was the name of of that telegram was drive object 1. Like that's what that is. So we got to do the same thing here. We want to have the main conveyor, right? We're wanting to tie that into the main conveyor. We might want the filler conveyor as well, but we might want to gear into both. And just showing that you have the option to gear into both a position, a speed, position, and a synchronous. So you can sync onto a sync. Because one of the things about these technology objects, and maybe I haven't mentioned before, that as you move up into the complexity, it starts with the speed axis. A position controller adds on to a speed axis, and so it adds functionality onto a speed axis. And so then a synchronous axis adds functionality onto a positioning axis, which already has the speed axis in it. So it kind of is like these babushka nestling dolls or whatever. And so a synchronous has everything that all the others do. And so that's why you can sync to a sync. So for our stuff, let's go through and I'll show you the mechanics. So let's go to the main conveyor and let's go to mechanics. And one of the things that I kind of talked about is we need to talk about this basic parameters. So is this axis a linear axis or is it a rotary axis? And so what that means is at the end of the day, are we wanting to be in linear units or are we wanting to be in rotary units? And the big, like in this bottle cup filling, you're like, oh, well, we want linear, right? Because we want the axis to like go down and move down 100 millimeters, whatever, like that. So, but this system is probably on a big rotary type thing. Like overall, yes, our values would be really nice to be in linear units and say, hey, I want to move forward and backwards a millimeter. But the way that the motion actually works is a continuous circle. And what that means is if you have a continuous process to where it's continuously running in one direction, if you set up a linear axis, you are probably going to at some point run into a what's called a rollover condition. You're going to run so many linked units out that you're going to have to deal with a rollover. Now, Portal does a pretty good job of doing that. So yeah, you can set it up, but what happens in the transition of those rollovers, you have to keep up with stuff and you have to and absolutely it can do it. But sometimes it's just easier to sit and say, hey, I have a big rotary machine. I have this big overall, everything in here is broken up into, I have 50 meters of belt. And so I'm going to set this up as a rotary axis. And yeah, it complains about it. I'm going to set it up as a rotary axis, and then I'm going to do what's called enable modulo. And so modulo is, on the simplest form, it's, I have 360 degrees in a rotation, right? And because a rotary axis is in degrees and degrees per second, I guess you could do it in radians if you really wanted to, but the basic unit is one rotation is 360 degrees. And so if you want to reset every 360 degrees, you set your modulo to 360 degrees. Okay. Well, if you figure out, oh, hey, my 50 meter thing is actually a million degrees, you could set this to a million degrees. And what that'll do is that will, one full rotation of your machine is broken up into a million degrees. And that means you're never going to have to be worried about any sort of rollover condition, like start, stop, like power up, power down, any sort of those things, because everything's in degrees, everything's kind of like synced up in degrees. And again, there absolutely is rollover for linear axis, but in general, you run into problems if you have a continuous process machine and you are running and have it set up in linear. Now, you say, well, then how do I set my bottle ratio or whatever if I want my operator doesn't need to convert like degrees of the machine? Like, that doesn't make sense. Well, you convert, that's just going to be a linear, that's just going to be a number that you multiply by. And if you're familiar with any of my streams or my videos about like these motion control functions, I use a winder program that we actually build and design and like sell. And in it, all of the motion control numbers are in degrees, but the product is in linear feet. So like they're winding up feet of paper onto a roll. And so there's just a number that if you want to go from feet to degrees, you multiply by that number, and it's just set. We set it at the beginning. We set it anytime you change a gear ratio, whatever, like you have to change that number. And then if you want to go from degrees to feet, it's the inverse of that. It's just a different number, and you just multiply those numbers depending on which direction you want to go. So we're going to leave this like this right here, and then we're going to go through all these other ones. So that's that basic parameters. Let's talk about mechanics before we go on to that. We talked about this before, that we're using these encoders. Is the encoder on the motor shaft, or is it on the load side? So look at this difference between the two of this. So on the motor, your motor RPM is being seen. On the load side, it means it's after the gear ratio. So whatever gear ratio you put in on down here, so whatever gear ratio you put in, your speed of your motor, the set point it's sending out to the drive, is actually going to be different based on this. And then you have what's called an external measuring system, which has its own gear ratio, which sounds complicated, and it is. We're going to go and just say on the motor shaft, because that's kind of what we're used to, right? We're also just going to leave this is the drive mechanism. So this is this total overall gear ratio to, in this case, because we're on a rotary system, this gear kind of out at this end is the load gear. And so that is the load system. So load units are going to be from 0 to 360 degrees. So this is degrees on this wheel out here. And this is kind of the difficult part to kind of make through. But degrees of shaft times your ratio equals load gear. Or sorry, load degrees. Now, there might be a pulley on this shaft going to a gear. So it's your total gear ratio. So 1 degree on your motor equals how many degrees on your actual final load. That's the concept there. In ours, we're just going to use 1-to-1. Okay. And let's go through and just click over on these other ones. Change all these others to rotary. And then we would want to do modulo on that too, but yeah, I mean, I guess we could do same modulo range. 1, is that enough zeros? 0.0. All right. So put that there and then do our last one, filler axis. So our filler axis, we actually want to be a linear axis because we want to tie at some point in our linear or in our rotary, we're wanting to tie linear to this. So we've got a linear, yeah, so we're good there. And there is no modulo. So, all right, so it's linear and we're good there. So let's save this. Now, what I want to do from here is go through and take a little time to set up a, what's it called? Set up the actual control for it. And we've done this before. We've done it before and we've gone through and set these things up like this, but I kind of want to do a little bit of actual programming to it so that the members can have a little bit of value for their membership for the programming level. I want to, and really for the other level as well. So just kind of like I want to write a block that kind of combines in these different like MC power, MC reset blocks. But we're going to do that towards the end of the stream. Right now, honestly, I really have to pee. I don't know about you guys. So I'm going to pause for a second, run in here, pee, and then come back. I've been drinking too much water, too much coffee. I've been going for 2 hours. So if you need to take a break, and we'll be back in like 30 seconds. So we're going to go to this. All right. That's quick being back. I was dying. All right, so we are back in a groove, and what we're going to be doing from here is I'm going to show you how to set up these MC gearing blocks, kind of going through individually on them. Make sure that got set up here. Oh, so much better. I was in pain. Yes, thank you, Ollie Reza. Thank you for staying. Thank you for staying around. So, all right, let's go through and I'll show you. Let's make a new block, and this right now, let's just do. So we're just doing a function call. I did do a function call, right? Yes. And what we will do, and if you're not familiar with like function calls, like difference between function calls, function blocks, like organizational blocks, all that stuff, I've got a bunch of edited videos that go through kind of like, yeah, the basics of those. But I figure most of you guys are here because you're probably have a little bit of experience with that stuff, and you're wanting to know about specifically motion control stuff. So one of the things that we're going to do here in a second is we're going to make kind of like a drop-in block that controls MC power, MC reset, and MC home. Okay, so kind of like a axis setup block. And so we're going to make that at the end of the stream. So we're not going to put in MC power, MC halt. So what we would do for this one, so is cup conveyor control. So let's just have like a move velocity. Is that the one that we want to use? So here's a I'll show you a little bit of difference. So cup conveyor MC velocity dB. And we're just going to drag our main conveyor in here. So that pretty much would work. So here's the thing. I want to show you a little bit of difference between, real quick, MC move and MC velocity. The cup. MC dog dB. So let's bring this up. Control 5. So just compare these two. We can have the same axis connected to them, but here's a little bit of a problem. So the MC move velocity function is what's called an edge controlled function. And so you activate it and then it runs. And then it only gets updated on activation. So like this velocity, this would be for this axis would be these are in their engineering units. So this velocity for the main conveyor axis would be in degrees per second. So 100 degrees per second, and you fire it. So let's say fire, you execute this function and you hold down the execute, it starts to move, and it moves at 100. It moves at a 100 degrees per second. Well, you're like, oh, I want to move a little bit faster. Well, in order to move at 110 degrees per second, you would have to execute a new move. It would have to be positive edge. And in order to actually change that velocity, it doesn't get updated. Well, you absolutely can go through, and there's a function or a block, a property, I guess I should say, in these called So we're going to do like move. And we'll just make conveyor. Well, this. And then we're just going to define this tag. Again, this is... don't like doing it this way, but this is just to kind of prove a point right now. Again, all of your set points and settings and stuff like that, you want to have in a data block so you can retain them, which means when you turn power off, they will actually come back up and they will actually be there the way your machine was. If you do everything in memory, guess what? Nope, it's gone. So don't do that. Use data blocks. But wanted to show you, so this is going to be main conveyor axis dot override, I think. Override dot velocity. Oh, I guess I didn't set that to proper rebar tag. Needs to be a real, I think, or maybe a L real. I think it's an L real. There it is. Yep, L real. So there's this thing called override, and by default, this thing needs to be 100 because no matter what your function is doing, like in these positioning moves, this MC velocity or the velocity override of your function is a percentage-based override. So if it's in the middle of a move, a lot of moves are these edge-controlled moves to where, in this case, velocity is going to run at 100 degrees per second until you execute a new move or stop the axis. Well, with the velocity override, if you wanted to run at 90 degrees per second, all you would have to do is change that velocity override from 100% to 90%, and because of our math, it would slow it down. So it would slow it down to 90 degrees per second. So the velocity override is the way that, like, if you were in the middle of like a camming move, for example, and or a very long absolute move or a very long relative move, then you would go through and you say, hey, I'm running this really long relative move. I want to change to different speeds. You would just change this velocity override and it would change to different speeds during the velocity override or during the move. So MC move velocity, that's how you would change the velocity in the middle of the move. Well, MC jog is not edge triggered. It's a continuously updating value. So if you took this same velocity and you maintain this jog forward, so you're moving forward. Yeah, technically it says it's jog, but you're moving forward and you change the velocity, it is going to use this acceleration and deceleration here in order to change velocity up and down. And so in a way, I feel like most of the time, if you are going to be changing a velocity control move, just like a speed move, you probably want to use the jog command instead of the velocity command, just in my opinion, just because it gives you a little bit more intuitive control over how to do it. This velocity override, my goodness, it can absolutely jack you up, because that velocity override, if you set it to 0, it won't move and it won't complain. It'll just be like, hey, I'm good. And then it'll just never complete the move. And it will be infuriating if you sit there and like accidentally put somehow get a velocity override into 0. And oh, hey, guess what? If you use it like this, that cup conveyor override always starts at 0. So if you actually programmed it this way, where you had like this cup conveyor velocity override, it would always be set. Let me show you the proper way to do it, since some of y'all are going to be getting this file. I'm not going to give you bad code. Instead of doing this, let's make a new block, data block, call it cup conveyor data. Not conveyor. But by the way, hey, y'all that are getting all like that are going to be getting these files and everything, you're getting all of my typos too. So we make a cup conveyor data, and normally we would want to do like booleans at the top, bool 0, data type bool, and then have like, let's do there's two words of bools, and then you could have like ints. You would want like ints and then reals, just because it kind of like separates stuff out. But yeah, there's a lot of stuff here. We're using optimized data access, so you can just put ints and booleans and all that sort of stuff in together, and it not really matter. But you can't do some stuff if you don't have offsets. And so a lot of times you have to turn off optimized data access or optimized block access, and I'm talking about stuff that you don't care about. So cup, so now because I'm in cup conveyor data, I'm just going to say velocity override. Okay, and I want that to be an L real, right? And so now instead of using this right here, I can click on here, or I could just say cup conveyor data, and then velocity override, since that's the only L real in the thing. And look at that, that's so much better, because if I wanted to duplicate this line of logic, I could just go through and say Control C and like make a new block called filler conveyor data. It's all that same. Now I could just Control A, Control C, Control V. Whoops. Whoops. Oh, we're at 3 hours. All right, we gotta hurry up, because I've got a meeting at 2. So you can just copy this. So I did it the wrong way though. I should have done this. Control C. Whatever. You can copy them. I don't know why it's not wanting. It's like my computer's dying or something. Whatever. So you can copy them, and I mean, honestly, I could probably just Control CV here, and then rename. And then change properties. General. So there. Now those two are exactly the same, but because they're renamed, you can use kind of like this same thing here. Like if you had this, you could do filler conveyor data dot velocity override, and it's the same thing. And so that's how you would actually normally do this. So for the next 30 minutes, I'm gonna go through and talk real quick about, so like that's move jog, move absolute. So here we talked about the move absolute and move relative, but what I wanted to show you really is about these synchronous motions. So if you want to, about the move absolute, move relative, there's actually edited videos about how to actually use those. And what I want to show you is the gear in and the gear in position. And so actually cancel this because we're in the wrong axis. So let's make a filler convey or control function call. Yeah, whatever. Because we actually want to bring these in, and I want to pull these in here. And again, I'm running up against a hard stop in about an hour, so I'm trying to get some stuff. And if I don't get to this, everything on stream that I want to get to, I will definitely make it and give it to the members. And I may put like a members only post about this stuff. So let's look at synchronous motion. We're going to set up both filler gear in and I always want to name these because sometimes you want to actually just, you already have these data blocks that are being created, as you could probably see them getting created. I'll show you where they get created. So if you want to name these something logical, because there are times that you want to that you will want to access these, and if you don't name them properly, then you're gonna have a bad time. So now, master slave axis. So our master for both of these are going to be the main conveyor axis, because we can't even have it any other way. And so now our slave axis, who's actually going to be the filler conveyor, we're just going to drag these over. So obviously the execute is the, so we'll look at the two differences. We still have all of the information, like the velocity override, all the positioning, all of that stuff. Your in gear, busy, like command aborted error, all of that is all common between them. So let's look at the differences. We have these ratios that we talked about. Think of kind of again, the gear in, like we talked about, is you gear in positionally whenever, and then it's locked in a speed mode, even though it is 100% position controlled. And we look at the two differences. We talked about the sync positions. So master sync to slave sync. Yes, so these, they're for Simmet for these. I do believe there are, yeah, so you can use Simmet because Simmet has the drive profiles, or like the motor profiles for the drives that you can tie into these. So you can run this on a PLC sim, you can run these, and then you can have your drive profiles in Simmet. Good question, Aliraza. So talking about the master sync positions, a couple of the things. So this master start distance is pretty critical, because the master start distance is the amount of the distance on the master axis that the slave has in order to get synced. And what will happen is if this distance gets too short, then the axis will, the move will give you an error, and it won't fault it, or won't execute, because it says, hey, that's physically impossible. I can't accelerate that fast. And so that'll be an error ID here on that block. And the way that you use this gear in position block is you sit at some point, and with a gear in, when you activate it, it's going to sync up, it's going to go, because it doesn't really care about what it's doing. It's just getting, like, throwing a belt over that drive shaft. So, but with a gear in position, it has to sit and wait for that master position. So what can happen is you can have a situation to where either the master position has gone past this sync position and it's not a modulo axis. And so if it goes past it, it has to go all the way around and then come back, and then it'll start going. Especially if you have a sync direction. This is a shortest distance sync direction, I believe, is number 3. Don't make me a liar. Don't make me a liar, Portal. Let's see. Yes! Shortest distance. So 1, 2, and 3 on your sync direction. I talked about that before. If you have a sync direction of 3, or if you have a sync direction 3, that means it's going to go the shortest distance. So on like a modulo axis, it could absolutely run backwards. And so, like, if you only want it to run in the positive direction, like in our kind of cup filler case, if you don't want it to like go choo and like shoot backwards, then sorry for your ears on that. any headphone wearers, but that's kind of the effect that it would have when you're sitting there thinking that your bottling line is going to be sitting still, and then all of a sudden the top filler axis takes off running backwards. Like, so yeah, you don't want to do that. So positive direction means that it will only sync up in that running direction. But if you run past that, this master sync position, if you're already past it, and it is going to have to wait until it comes all the way around and comes back. So keep that in mind. Same thing with the slave sync position. If the slave can't kind of like get to that position, then it's just not going to work. So one of the things that I have on kind of the winders, and on the actual winder live stream that we did, I talked about the knife cutting. Well, I use an MC gear in position in order to do that. So I have a really long relative move and rolling up the paper. Well, the knife says, okay, its master is the metering roll, so that the rolling of the paper, and it's sitting something like this right here. And I say I have a point, it's not exactly random, but it's a point sometime in the middle of the roll to be like, all right, gear in, MC gear in position, execute. And it goes blip. And this little start sync right here goes positive. So it goes true. And then it just sits there. And in my case, as it rolls through, this point, we'll call it my ring here, is coming down the line, and that is the master sync position. And so I generate that master sync position here, and then my slave sync position, I set it 0 because I home my axis to this point. I home the knife, the actual knife blade, to be the 0 point. That's what I'm doing. And then all I'm doing is saying, put my knife, I want it at 120 degrees, or in this case, I want it to move 180, say 200 degrees. That's where my actual cut point is. So if this is 0, I want it at say 200 degrees, whatever it is. And then so as it's sitting here like this, and as this comes by, it goes pop and automatically hits. And I execute that function way back. So it's like the actual cut point is way down the line, and it's just sitting there waiting. And so it gets wound up. It comes in and goes, comes up and goes pop, pop, and hits same point. So that is the cut point. And so wherever that point is on my leading axis, I'm setting for 0. I want this axis to be at 200 degrees when my leading axis is at 1,000 degrees. And then I'm in sync. Okay? So that's how I physically use this. Well, in there is a the ratio. Well, that sync position sets it to where if I call it like a rip factor. If I want this to kind of like rip and like pull it through, I change that ratio. And so I make my slave axis run faster. So I make it like a 1 to 1.1 ratio. And so I get like a rip factor. So it kind of pulls the paper and shoots it off and tears it, because rotary knives need that. So that's kind of another example of this. So we would essentially get this, figure out like the first cup. Like we would home our position and create where this first cup is. And then we say, okay, we've got our home position on our cup. It's at 0. And then we could say home our filler conveyor. So our first filler needs to be right here, and it needs to be in the center of the cup. Okay, we've got 0 homed to this point here on our filler. And so now the way we want to sync up is we want to say, all right, we want to get this moving. So it goes off, goes away, and then says, all right, MC gear in pause and sync up to the conveyor. And you could do it a couple different ways. You could do it to where it speeds up and catches up to it and then says, all right, here we go. And it's in sync, right? Or you could sit there and say, like, it's way off and it's coming up, and you say, all right, I'm within 100 degrees or whatever. And then say, all right, I'm going to fire that function. And then when it comes by, it goes stink, and then just doop, and starts following. You can absolutely do it, set it up that way. And that's how you would use this function. So, and then we'll talk about the actual filler probe later. But I have promised one of you guys to talk about Telegram 750 in this context. And in this context, so Telegram 750 is what is called the additional torque data telegram. And I want to put it on to one of these axes real quick and show you what it does. So we're going to have to put it on, I guess we'll just put it on the filler conveyor. Because if our filler conveyor gets off, okay? If our filler conveyor gets to where it's slightly off, we don't want it to crash. We want to limit the amount of torque that is available for, if for some reason we get out of sync, we want to limit the amount of torque to be able to, like, we don't want to break a cup. So we're going to enable torque limiting on this axis. So let's do the conveyor. So we're going to do conveyor filler telegrams. And so we're going to add in a telegram here. And we're going to add in the supplementary torque telegram, which is Siemens telegram 750. We're going to save that. And because that is now in here, let me make sure that does Telegram 3 have the information we need for MC torque limiting? Telegram 3 speed. No, it does not. So it won't be able to use torque limiting, the actual MC torque limiting function. But what we can do, I'm going to show you what this does. And so in order to do this, the actual torque limiting, you would need to be using a Telegram 105. So there, or a Telegram 103, I think. So let's see. The Telegram current instantaneous. Yep, I think you could do a 103 and 105. Yeah, I think you could do either one. But you need the instantaneous current because we're going to be limiting the torque. But that's all you need to do. You need to add in the 750. So for this, let's just go through and change this to a 103. And you notice it gave a lot of different words. But that's as simple as it takes to convert different telegrams. It's just on this screen. We want this one running a 103. So let's go through now and look at what that does by adding that Telegram 750 to our conveyor cup. Do I need to be? Yeah, this is fun. Does not like something. That's funny. Okay. Actually, no. Let's go here. Upper loop. Torque limiting. Upper torque limit. Is it there? Or is it doing it in current limit? So this 750, let's look and see what this data actually is. I don't think it shows it on here though. Yeah, there it is. Yeah, so it ties this limit positive, so P1522, 1523. So why did that not... Did I pull up the wrong one? Oh, I put it on the wrong one. I'm like, what the crap? Why didn't y'all tell me? Why didn't y'all tell me? Come on, chat. That was your opportunity there to talk about how dumb I was. No, I pulled up the wrong one because we put that on the filler because we're wanting that filler conveyor. So let's go to torque limiting here, and now this is tied in. So this Profi drive PZD9, so this extra telegram is now tied in here to the upper torque limit. And I will say you can absolutely modify this torque limit like manually. The problem is if you have a have put a negative value here, you'll have problems. So I'm gonna highlight this little notice here and read it to you. A negative value on the output of the torque limit calculation can result in an unwanted behavior of the drive. For example, a runaway of the drive. And we always talk about we don't want our drives running away from us, right? So one thing that there is what's called an MC torque limiting block. It requires a telegram 103 or 105. It requires a specific telegram because it wants to see that value coming back for some reason in the 103 telegram. Don't ask me why, but because there should be in the 750, there is the torque actual value, But what it is wanting to do is to limit the actual current. And so it's wanting to see the current actual value. So 750 on return has torque actual, and then it has these positive and negative limits. And so then you have your additive torque that you can add in at P1511. And so how much time I got? I think in 20 minutes I can make a data type for Telegram 750. I think so, because we want to be able to use this function without. We want to be able to use this function like on the V90, for example, which doesn't have a 103. I lie, it does have 103. On maybe something that you want to use a Telegram 3, for example, and not use the MC torque limit function. If you're going to do that, you need to make sure that your limits, the positive limit is always positive. So do an absolute value before it. And then the negative limit, it's always negative. So absolute value and then -1. So you have to write that code into your functions. Otherwise, you're going to have a bad time if you activate that. So let's go through real quick and let's just make a Telegram 750. If I haven't, have I? I want to show you something, because do I have a Telegram 750? No, we made a Telegram 371. So let's do that. And by the way, again, at both membership levels of the channel, you get access to this library, and there's a little README in the Google Drive folder on how to access these library files. But you will need version 17 or above of TIA Portal in order to bring up this global library. But you would just say open, then download all of the folders, get that library, and then you would open it, and then you have access to all these. So again, that's available at both levels in the membership. So let's go through, and I'll show you how to use this library function. So I want to make a PLC data type. I'm going to add a new data type. I'm going to add tel 750 out. That looks like horrible. Out. And that is what is going. So we've got, let's look at our description. So that's PZD n+1. So that's just a word. Okay. So we've got 3 words. So what you could use this additional torque is as a percentage. And remember, all of these will be in percentages of, so it'd be in percentage of the reference value, which in this case, I think it's like 2003, maybe. So this is make sure this is right. Make sure this is right. Yep, positive, negative. Yep. Lower limit. Okay, so we're going to save that. We're going to toss this over in here. Tel 750 in. What is this? This is torque actual. That is an int. And that is actually it. So now I'm going to put these into the library. And now y'all get those. So, and what you can do now, since we have that on our filler, you can go and create a tag. Where's tags? Tags. So you can say filler torque in, and then we're going to take and grab our type. Tell 50 in. And I'm sure if you've been on this, you've seen me do this before, but we're about to tie these to the memory addresses. But this is how you use data types to kind of modularize your data. So so now we need to go to our actual 750 telegram. And so that is I-298 for both of them, or for 298 for both of them. So let's go. So for our, get out of here. So our in is going to be I-298.0. Our output is going to be Q298.0. And now if we wrote a block that worked on any telegram, right? We could do a function block that activates these torques. Again, we're going to sanitize the crap out of our values. And so what we would do is we would create a function block to where we say, hey, what's our telegram in? What's our telegram out? And our telegram out output, or the telegram out would be the output, telegram in would be an input. We'd bring that data in, and then we'd say, hey, activate torque limit, what's the torque limit, and like have those as inputs into the block, and then it modifies everything you need to do. And that's honestly what a technology object is doing, because as you can see here, there's what's called these actor interfaces. And so we have all of this data from our telegram that's in our data types. And so we haven't compiled that. We haven't compiled it, so it hasn't like updated the data type. But yeah, so here we go. We have this 750 telegram. So if we wanted to do this even outside of a MC function, all right, 10 minutes. Here's how we would use MC the 750 torque data, right? MC torque limiting, okay? And so we do filler MC torque okay. Now I am going to warn the ever living crap out of you guys. Okay. Oh, I'm going to warn you. And I'm showing you this block. This block, it's a little sketchy. And here's why. So we could put our axis block, so our filler conveyor, put that there. All right. And this block looks so easy, right? So our limit is going to be like a positive value. It's going to be clamped, like it's going to enable this, like, yeah. So that is in Newton meters, and it's scaled into like whatever's in your value. So that scale is like in engineering units. The problem is though, I'm going to show you this on the thing. There's like this little where is it? It's like this little warning. So where's the warning? The warning is there. Requirements for fixed override response. There's a warning that's like, oh hey, if you're in if you change out of a positioning move, Like if you just drop this off and you're in the middle of a positioning move, it goes crazy. And it's because it's deactivating the following error. Okay? So it kind of talks about this, and this is a Motion 102 class topic, talking about following error and how all these different things. This was a concepts level, but what happens if you limit the torque in a position controlled move, you will build up what is called following error. So you are absolutely okay to use this 750 telegram, but if you are in a position controlled move and you are using this telegram 750, then what's happening is it's building up this following error. Because if you're in torque limit, that means it's trying to run faster than it is. And what a following error is the position you are at is not the position you are supposed to be. You are not following correctly. So, best case, you get a following error fault and it faults out. Well, what happens with this MC torque limiting is it disables that fault. It says, oh, hey, I'm in MC torque limiting. I'm going to have a following error. All right. But then if you just go and flip off the MC torque limiting, all of a sudden you have this really big following error sitting there on your position axis. So what happens is all of a sudden that drive goes, holy crap, I've got to be up here. And sorry for your ears again, but it'll shoot up and speed up really quickly, and it can absolutely break a piece of equipment, because during following error correction, your limits are not really controlled. And it sounds horrible, but the speeds that you can and accelerations that you can get in a following error correction are higher than what you can get in a normally controlled move. So what happens is if you are wanting to run a position controlled torque limited move, then you have to keep the torque limiting block on all the time. So what you can do is tie in either the command aborted or the command aborted, the not busy. Basically, if for whatever reason, like a position controlled move stops, then you're still running that torque limiting. Like the torque limiting has to be on. And if you are in a position controlled move, like whatever it is, then, and so like, actually, I want to say that there might be a, in position control. So like, yeah, positioning. So this right here is a bit. Just why is it not there? So this little bit here, I'll show you that is a status that is in the motion status or error. Like there's a status there for positioning, and you can look at that and you can make it to where that MC torque limiting will not turn off if it's in a positioning move. So basically whatever your on off command is, once it comes on, if it's in positioning, you do not want to let it off. So Nikos has got a question. It says, isn't torque limit much greater than the torque normally required for the position control? Yes, normally the torque limit needs to be up high. Like it needs to be high, because otherwise you're not going to be able to move, right? You have this whole system that you're trying to move back and forth, and you need that torque. Or there absolutely are tons of reasons why you would want to be in torque control. For example, in the little help file, it was talking about what's called a fixed end stop. And what it does is it says, okay, I have some sort of probe. I'm an alien in Kansas, and I have a probe, and I want to put a certain amount of pressure on my probe. But I don't want it to slip, right? I don't want it to go through. And so if it goes through, I want to fault out, or if this thing moves, I want it to fault out. And that's called a fixed end stop. And so what you could do is you say, hey, I don't want to hurt this object, or I don't want to hurt my probe. So my motor can put out 20 Newton meters of torque, but if it puts out 20 Newton meters of torque, it's going to break my probe. So I only want it, I'm going to activate what's called travel to a fixed end stop, and I'm going to, in that time, limit the amount of torque to, say it can only handle 5 Newton meters of torque. You say, I can put 5 Newton meters of torque up here, but that's it, because I don't want to break my probe. But then if this moves, something's wrong, and so I want to be able to detect the position. And so I want to do a position controlled move up to, say, 5-10 millimeters, and then I want to limit the torque. And it says, all right, torque and limitation, that I know that means I'm pushing up against my wall. So that is that's what a fixed end stop is. Normally, we've talked about synchronous or load sharing applications, like for winders or belts and things like that. That's normally when we've done that, and those aren't position controlled moves normally. And so you can everything we've talked about before has been speed control moves, and I will show you real quick while I'm talking about that. Even the velocity and jog functions. What was that in this cup conveyor? You notice by default down at the bottom of here, they are position controlled moves. I got in trouble the first time I used MC torque limiting because I did not realize that an MC jog is actually a position controlled move by default. So on these, if you are not wanting all the following error and calculation and position controlling and all of that, and you just want it to run at a velocity, false, and then false. And then if you're running this NC jog, you don't have to worry. You can actually turn on and off the torque limiting in that function. So it's kind of cool. The problem that I ran into was actually on a winder, and that mandrel is running in a jog, and it's running in a jog, but I had it torque limited, and then at the very end of the roll, it needs to do what's called a tail position. And so it needs to like have the cut, it comes off, and then it goes zoot, and then makes a move. Well, that's all based on timing. And I didn't realize that to where that jog, and so I just turned off the torque limit, and it went whee, and they had to replace the mandrel. So because it went way too fast. So all that to say, a torque limiting during a positioning move is required sometimes. But if you just use this kind of tag over here, and you don't disable these following error problems, then what happens is you get what's called following error, because you're going to push up against it and it's wanting to move, but then it can't. And that's what a torque limit would do. So I'm probably going to see it later, but Ignatius, thank you for joining. And yeah, so yeah, Lucid, any sort of probing is yeah, it's automatic. If the probe has reached, then yes, the drive faults automatically. But yeah, so we're going through, and I'm running up against my hard stop. So what I'm gonna do is before the next live stream, or at some point in the future, maybe this afternoon, I'm going to make a little block that's going to be a little setup block that brings in your axis, and it controls the MC power, MC reset, and MC home. That way you could just pull in one block, connect up your axis, and then you're good to go. And that'll be available. That'll be available in the archives for both tier levels for this. That sort of stuff is something I definitely want to be able to supply to you, and I'll probably fill out a little bit more of this with the different functions and everything for the programmer levels. So I'll be updating that probably by the end of the day. If not, it'll be over the weekend. But yeah, all that to say, I want to thank everybody that has taken part of this stream and that's been in chat. If you're watching on demand, again, thank you for finding or being a part of this community. We've got the Discord. If you want to reach out, join that. That's cool. We've got a cool international crowd there. But yeah, appreciate everyone. And again, if you're coming on and you've made it this far, why don't you at least like the video, because that's going to get it out there, and it's a simple way to support us. And if you like this type of content, subscribe, because we do this, try to do it every week. The next month or so, I'm probably going to be a little off. I may end up actually doing a live stream from a plant, from my van, using my, oh yeah, the wall definitely moves. Because that wall is definitely not a wall. But yeah, I probably be doing at least a couple of live streams from the van in with Starlink, and of course the members have seen the inside of my van. I don't think anybody else has seen the inside of my van, but yeah. Anyway, I appreciate everyone that has come in, and for the members that have joined during this stream, again, I thank you as much. And yeah, also, here's all of the current members. I got to update this, and that's awesome. I appreciate everyone, and y'all have a blessed weekend and have an awesome time. Y'all take it easy.